Picture this: two galaxies, locked in a cosmic dance, colliding with such force that they reshape the very fabric of space and time. This is not science fiction, it's the Antennae Galaxies, a pair of galaxies so strange and mysterious that they defy everything we thought we knew about the universe. What if I told you that within these galaxies there are phenomena so bizarre, so inexplicable, that even the brightest minds in astronomy are left scratching their heads? From supermassive black holes locked in a gravitational tango to cosmic fireworks lighting up the darkness of space, the Antennae Galaxies are a treasure trove of cosmic oddities. But here's the kicker: these phenomena aren't just fascinating, they're rewriting the rules of astrophysics as we know it. By the end of this video, you'll uncover 50 of the strangest, most mind-bending mysteries hidden within these galaxies, each one more astonishing than the last. So, are you ready to dive into the unknown and explore the secrets of the Antennae Galaxies? Let's begin. Now, let's zoom in on the very heart of the mystery, the collision itself. The Antennae Galaxies are not just any galaxies. They are the result of two massive galaxies smashing into each other in a cosmic spectacle that has been unfolding for hundreds of millions of years. This isn't a quick crash, it's a slow, dramatic merging that has twisted and stretched the galaxies into their current, peculiar shape. Imagine two spirals of stars, gas, and dust, each billions of times more massive than our Sun, spiraling closer and closer until gravity takes over, pulling them into a chaotic dance. The result, a stunning, almost surreal structure with long, sweeping tails of stars and gas that stretch across space. These are the antennae that give the galaxies their name. But this collision isn't just about destruction, it's also about creation. The immense forces at play compress gas clouds, triggering bursts of star formation on a scale rarely seen elsewhere in the universe. This is where the bizarre begins, where the chaos of the collision gives birth to phenomena that challenge our understanding of how galaxies evolve. From the formation of massive star clusters to the creation of entirely new cosmic structures, the collision of the Antennae Galaxies is a cosmic laboratory, revealing secrets about the universe that we're only beginning to unravel. Now, let's turn our attention to the very heart of the Antennae Galaxies, a place where gravity reigns supreme. At the core of this cosmic collision lies not one, but two supermassive black holes, each billions of times more massive than our Sun. These titans are locked in a gravitational dance, orbiting each other in a slow, mesmerizing spiral that will eventually lead to their merger. But this isn't just a cosmic ballet, it's a spectacle of immense power and strange phenomena. As these black holes circle one another, they warp the fabric of space-time around them, creating ripples that can be felt across the galaxies. Their immense gravitational pull doesn't just affect nearby stars and gas, it also generates intense radiation, heating the surrounding material to millions of degrees and producing some of the brightest X-ray emissions in the universe. But the strangest part, this gravitational tug-of-war can fling stars and gas clouds out of the galaxies entirely, creating streams of material that stretch far into intergalactic space. And as these black holes inch closer to their eventual collision, they release bursts of energy so powerful that they can outshine entire galaxies. This duo is a testament to the raw, chaotic forces at play in the Antennae Galaxies, offering us a glimpse into the extreme physics that govern the universe. The dance of these supermassive black holes isn't just a cosmic curiosity, it's a key to understanding how galaxies evolve and how the universe itself is shaped by the most powerful forces imaginable. Now, shifting our gaze from the gravitational chaos at the galaxy's cores, let's zoom in on one of the most dazzling features of the Antennae Galaxies, their hyperactive star formation. Imagine a cosmic factory working at full throttle, churning out stars at a pace that dwarfs anything we see in our own Milky Way. This is exactly what's happening here. The collision of the two galaxies has triggered a frenzy of star birth, creating vast regions where gas and dust are compressed, heated, and ignited into new stars at an astonishing rate. These star-forming regions, often referred to as starbursts, are so intense that they produce hundreds of stars every year, a stark contrast to the Milky Way's more modest rate of just a few stars annually. But what makes this process so extraordinary isn't just the sheer number of stars being born, it's the sheer scale of the activity. Massive clouds of gas, some spanning hundreds of light years, collapse under their own gravity, igniting clusters of young, hot stars that shine with incredible brightness. These newborn stars are often much larger and more luminous than those in common galaxies, and their intense radiation lights up the surrounding gas, creating glowing nebulae that paint the galaxies in vivid hues of blue and pink. However, this rapid star formation comes with its own set of consequences. The intense radiation and stellar winds from these young stars can blow away the very gas clouds that gave them life, effectively shutting down future star formation in those regions. It's a cosmic catch-22. The very act of creating stars can starve the galaxy of the raw materials needed to make more. Additionally, the frequent supernova explosions that accompany such active star formation can further disrupt the surrounding environment, sending shockwaves through the galaxies and triggering even more star birth in a chaotic cycle of creation and destruction. This hyperactivity isn't just a spectacle, it's a window into how galaxies evolve. The Antennae Galaxies show us what happens when cosmic forces collide, driving star formation to extremes and reshaping the galaxies in the process. As we continue to explore these starry nurseries, we gain a deeper understanding of the delicate balance between creation and destruction that shapes the universe itself. Now, as we move from the dazzling star-forming regions, let's turn our attention to one of the most striking visual features of the Antennae Galaxies, their colossal tidal tails. These vast, sweeping arcs of stars, gas, and dust stretch across space for hundreds of thousands of light years, resembling the graceful tails of celestial comets. But these aren't just beautiful cosmic decorations. They're the direct result of the immense gravitational forces unleashed during the collision of the two galaxies. When galaxies collide, their gravitational fields interact in complex ways, pulling and stretching material into long, flowing streams. In the case of the Antennae Galaxies, this process has created two massive tidal tails that extend far beyond the main bodies of the galaxies. These tails are essentially the remnants of the galaxy's original structures, torn apart and flung outward by the sheer force of the collision. But tidal tails aren't just debris, they play a crucial role in shaping the future of the galaxies. As material is pulled into these tails, it can eventually fall back into the galaxies, fueling new rounds of star formation. In some cases, the tails may even give birth to entirely new dwarf galaxies, adding another layer of complexity to the galactic ecosystem. What's truly fascinating is how these tidal tails act as cosmic time capsules. By studying the composition and motion of the material within them, astronomers can piece together the history of the collision, tracing the movements of the galaxies over millions of years. The tails also provide a unique laboratory for understanding how gravity shapes the universe on the largest scales, offering insights into the forces that drive galactic evolution. As we observe these majestic tidal tails, we're reminded of the dynamic and ever-changing nature of the cosmos. They're not just remnants of a violent past, they're also harbingers of a future where the Antennae Galaxies will continue to evolve, merge, and transform in ways we're only beginning to understand. Now, shifting our gaze from the sweeping tidal tails, let's tune into something invisible yet equally fascinating: the mysterious radio emissions emanating from the Antennae Galaxies. These radio waves, detected by powerful telescopes, are not just random noise. They're signals that hold secrets about the galaxy's inner workings and the chaotic processes unfolding within them. Radio emissions in space often come from high-energy events, and the Antennae Galaxies are no exception. The collision of these two galaxies has created a hotbed of activity, from supernova explosions to the interactions of supermassive black holes. These events generate intense radio waves which travel across the cosmos and reach our telescopes here on Earth. But what's intriguing is that some of these emissions don't have clear explanations, leaving astronomers puzzled. One potential source of these mysterious radio waves is the supermassive black holes at the cores of the galaxies. As these black holes consume matter, they emit powerful jets of particles and radiation which can produce strong radio signals. However, not all the emissions match the expected patterns from black hole activity, suggesting there might be other, less understood processes at play. Another possibility is the intense star formation occurring in the Antennae Galaxies. When massive stars are born and die in rapid succession, they release enormous amounts of energy, some of which is emitted as radio waves. The chaotic environment of the colliding galaxies amplifies this process, creating a complex web of radio signals that scientists are still trying to decode. What makes these radio emissions particularly valuable is what they reveal about the structure of the Antennae Galaxies. By mapping the sources and patterns of these waves, astronomers can peer into regions obscured by dust and gas, uncovering hidden star-forming areas and tracing the flow of material between the galaxies. This information helps paint a clearer picture of how galactic collisions reshape the universe. As we listen to these cosmic whispers, we're reminded that the Antennae Galaxies are not just a visual spectacle. They're also a symphony of invisible signals, each one telling a story of creation, destruction, and transformation. And while many questions remain, these mysterious radio emissions continue to guide us toward a deeper understanding of the universe's most dramatic events. Now, as we venture deeper into the mysteries of the Antennae Galaxies, let's turn our attention to something that's both invisible and enigmatic: dark matter. This elusive substance, which makes up a significant portion of the universe, plays a crucial role in shaping galaxies, and the Antennae Galaxies are no exception. However, what astronomers have discovered here is far from ordinary. The distribution of dark matter in these colliding galaxies is unusual, challenging our current understanding of how cosmic structures form and evolve. Dark matter doesn't emit, absorb, or reflect light, making it invisible to traditional telescopes. Yet, its presence is felt through its gravitational effects on visible matter like stars and gas. In most galaxies, dark matter forms a halo-like structure, enveloping the visible components and providing the gravitational glue that holds everything together. But in the Antennae Galaxies, this distribution appears to be uneven and irregular, defying the patterns we've come to expect. One possible explanation for this anomaly lies in the violent collision that brought these two galaxies together. As the galaxies merged, their dark matter halos interacted in complex ways, potentially creating clumps and voids that deviate from the smooth, symmetrical halos seen in isolated galaxies. This chaotic redistribution of dark matter could be influencing the galaxy's overall structure, affecting how stars and gas move and interact within them. Another intriguing aspect is how this uneven dark matter distribution impacts the galaxy's gravitational lensing effects. Gravitational lensing occurs when massive objects, like galaxies, bend the light from objects behind them, acting as cosmic magnifying glasses. In the Antennae Galaxies, the irregular dark matter distribution could create unexpected lensing patterns, offering astronomers a unique opportunity to study how dark matter behaves in extreme environments. What makes these dark matter anomalies particularly fascinating is what they reveal about the nature of dark matter itself. If dark matter behaves differently in colliding galaxies than in isolated ones, it could provide clues about its properties and interactions. For instance, does dark matter interact with itself in ways we haven't yet detected? Or could there be different types of dark matter with varying behaviors? These are questions that the Antennae Galaxies are helping scientists explore. As we piece together the puzzle of dark matter in the Antennae Galaxies, we're reminded that the universe is full of surprises. Even the invisible forces shaping our cosmos can behave in ways that challenge our assumptions, pushing us to rethink what we know about the building blocks of the universe. And as we continue to study these anomalies, we edge closer to unraveling one of the greatest mysteries of all: the true nature of dark matter. Now, let's shift our gaze to one of the most dramatic and explosive events in the cosmos: supernova explosions. In the Antennae Galaxies, these cosmic fireworks are not just occasional spectacles. They're a regular occurrence, lighting up the chaotic landscape of these colliding galaxies. But what exactly causes these frequent supernova, and how do they shape the environment around them? Supernova are the explosive deaths of massive stars, marking the end of their life cycles in a blaze of glory. In the Antennae Galaxies, the collision between the two galaxies has triggered an intense burst of star formation, leading to an abundance of massive stars. These stars burn through their fuel quickly, living fast and dying young. When they exhaust their nuclear fuel, their cores collapse under their own gravity, resulting in a cataclysmic explosion that can outshine an entire galaxy for a brief moment. The frequency of supernova explosions in the Antennae Galaxies is staggering. Astronomers have observed multiple supernova occurring within relatively short periods, a testament to the galaxy's hyperactive star-forming regions. Each explosion releases an enormous amount of energy, ejecting heavy elements like iron, gold, and uranium into space. These elements, forged in the hearts of dying stars, are scattered across the galaxies, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. But the impact of supernova goes beyond just creating cosmic glitter. The shock waves from these explosions ripple through the surrounding gas and dust, compressing it and triggering the formation of new stars. In a way, supernova are both destroyers and creators, ending the lives of stars while seeding the birth of others. This cycle of destruction and creation is a key driver of the Antennae Galaxies' ongoing evolution. Supernova also play a crucial role in shaping the galaxy's structure. The energy released by these explosions can heat the surrounding gas, preventing it from collapsing to form new stars. In some cases, this can lead to the formation of vast bubbles of hot gas, which expand and interact with the galaxy's magnetic fields, creating complex and dynamic environments. These interactions can influence how stars and gas move within the galaxies, adding another layer of complexity to their already chaotic nature. What makes the supernova in the Antennae Galaxies particularly fascinating is how they reflect the galaxy's turbulent history. Each explosion is a reminder of the intense forces at play in this cosmic collision, offering astronomers a glimpse into the life cycles of stars and the processes that shape galaxies. As we continue to study these explosive events, we gain a deeper understanding of the delicate balance between destruction and creation that defines the universe. With each supernova, the Antennae Galaxies remind us of the incredible power and beauty of the cosmos. These explosions are not just fleeting moments of light. They are the building blocks of galaxies, the engines of cosmic evolution, and the storytellers of the universe's grand narrative. And as we witness their brilliance, we're reminded that even in destruction, there is the potential for new beginnings. Now, let's turn our attention to another fascinating feature of the Antennae Galaxies' cosmic dust clouds. These dense, swirling masses of dust and gas are more than just cosmic fog. They play a critical role in shaping the galaxy's structure and fueling their ongoing evolution. But what exactly are these dust clouds and why are they so important? Cosmic dust clouds in the Antennae Galaxies are vast regions filled with tiny particles of carbon, silicon, and other elements. These particles, often no larger than a grain of sand, are scattered throughout the galaxies, creating thick, opaque clouds that can block visible light. This makes certain areas of the galaxies appear dark and mysterious, hiding the stars and other celestial objects behind them. However, these clouds are far from empty. They are bustling with activity, serving as the birthplaces of new stars. The collision between the two galaxies has compressed these dust clouds, triggering intense star formation. As the clouds collapse under their own gravity, pockets of gas and dust begin to heat up, eventually igniting to form new stars. This process is particularly active in the Antennae Galaxies, where the collision has created a chaotic environment ripe for star birth. The dust clouds act as cosmic nurseries, providing the raw materials needed to build stars and planetary systems. But the role of cosmic dust clouds doesn't end there. These clouds also play a crucial part in absorbing and re-emitting light. While they block visible light, they are excellent at absorbing infrared radiation. This means that even though some regions of the galaxies appear dark to our eyes, they glow brightly in infrared wavelengths, revealing hidden star-forming regions that would otherwise remain invisible. This ability to absorb and re-emit light makes cosmic dust clouds essential tools for astronomers studying the galaxy's structure and evolution. Interestingly, the dust clouds in the Antennae Galaxies are not evenly distributed. Some regions are thick with dust, while others are relatively clear. This uneven distribution creates a patchwork of light and shadow, adding to the galaxy's dramatic and chaotic appearance. The densest clouds are often found in the galaxy's tidal tails, where gravitational forces have pulled material away from the main bodies of the galaxies, creating long, trailing streams of dust and gas. As we study these cosmic dust clouds, we gain a deeper understanding of how galaxies evolve. They are not just obstacles to our view, they are active participants in the life cycle of stars and galaxies. By observing how these clouds interact with light and how they contribute to star formation, we can piece together the complex processes that drive the evolution of the Antennae Galaxies and other cosmic structures. The cosmic dust clouds in the Antennae Galaxies remind us that even the darkest corners of the universe hold the potential for creation. They are the hidden architects of star formation, the silent builders of galaxies, and the unseen storytellers of the cosmos. And as we peer through their veil, we uncover the secrets of how galaxies like the Antennae come to life. Now, shifting our gaze to another extraordinary feature of the Antennae Galaxies, we encounter the enigmatic X-ray binary systems. These cosmic duos are among the most energetic and fascinating phenomena in the universe, offering a glimpse into the extreme interactions between stars and their compact companions. But what exactly are X-ray binary systems, and why do they captivate astronomers so deeply? An X-ray binary system consists of two celestial objects locked in a gravitational dance, a normal star and either a black hole or a neutron star. As these two objects orbit each other, the intense gravitational pull of the black hole or neutron star strips material away from its stellar companion. This stolen material spirals inward, forming a swirling disk of superheated gas around the compact object. As the gas heats up to millions of degrees, it emits powerful bursts of X-rays, lighting up the surrounding space like a cosmic beacon. In the Antennae Galaxies, these X-ray binary systems are particularly abundant, thanks to the chaotic environment created by the ongoing galactic collision. The collision has triggered a surge in star formation, producing many massive stars that eventually collapse into black holes or neutron stars. These compact remnants then pair up with other stars, creating a high number of X-ray binaries. The result is a galaxy teeming with these high-energy systems, each one a miniature powerhouse of radiation. What makes these systems so intriguing is not just their brightness but also the extreme physics at play. The intense gravitational fields near black holes and neutron stars warp space and time, creating conditions that challenge our understanding of the universe. For example, the material in the accretion disk around a black hole can reach speeds close to the speed of light, generating X-rays so intense that they can outshine entire galaxies. Meanwhile, neutron stars, with their incredibly dense cores, can spin hundreds of times per second, producing regular pulses of X-rays that act like cosmic lighthouses. Studying these X-ray binary systems in the Antennae Galaxies provides valuable insights into the life cycles of stars and the behavior of matter under extreme conditions. By observing the X-rays they emit, astronomers can measure the properties of black holes and neutron stars, such as their masses and spin rates. This information helps us understand how these objects form and evolve, as well as their role in shaping the galaxies they inhabit. Moreover, X-ray binaries are not just isolated phenomena, they are part of a larger cosmic ecosystem. The energy they release can influence the surrounding gas and dust, triggering new waves of star formation or heating the interstellar medium. In this way, X-ray binary systems contribute to the dynamic and ever-changing nature of the Antennae Galaxies, adding another layer of complexity to their already intricate structure. As we continue to explore these high-energy systems, we uncover more about the forces that drive the universe. X-ray binary systems remind us that even in the vastness of space, the interactions between two objects can have profound and far-reaching consequences. They are a testament to the power of gravity, the resilience of matter, and the endless surprises that the cosmos has in store. And in the Antennae Galaxies, these systems shine brightly, offering a window into the extreme and the extraordinary. Now, turning our attention to another fascinating aspect of the Antennae Galaxies, we delve into the phenomenon of galactic cannibalism. This process, where larger galaxies consume smaller ones, plays a significant role in shaping the unique and bizarre features of the Antennae Galaxies. But what exactly is galactic cannibalism, and how does it influence these colliding galaxies? Galactic cannibalism occurs when a larger galaxy, like one of the Antennae pair, gravitationally pulls in and absorbs a smaller neighboring galaxy. This process is driven by the immense gravitational forces exerted by the larger galaxy, which can strip away stars, gas, and dust from the smaller one. Over time, the smaller galaxy is completely assimilated, its material becoming part of the larger galaxy's structure. In the case of the Antennae Galaxies, this process is amplified by the ongoing collision between the two main galaxies, creating a chaotic environment where smaller galaxies are more easily consumed. The effects of galactic cannibalism are profound. As the Antennae Galaxies consume smaller galaxies, they gain additional material that fuels star formation and contributes to the already intense activity within these galaxies. The influx of new stars, gas, and dust from the consumed galaxies can trigger bursts of star formation, adding to the vibrant and dynamic nature of the Antennae Galaxies. This process also helps explain the presence of unusual star clusters and the rich, complex structure of the galaxies. Moreover, galactic cannibalism can lead to the formation of tidal tails and other distinctive features. As smaller galaxies are pulled apart, their material is stretched out into long streams, creating the dramatic tidal tails that are a hallmark of the Antennae Galaxies. These tails are not just remnants of the consumed galaxies, they are also regions where new stars can form, adding another layer of complexity to the galaxy's structure. The process of galactic cannibalism also has implications for the evolution of the Antennae Galaxies. By consuming smaller galaxies, the Antennae Galaxies grow in size and mass, altering their gravitational influence and shaping their future interactions with other galaxies. This ongoing process of growth and transformation is a key factor in the evolution of galaxies throughout the universe. In the Antennae Galaxies, galactic cannibalism is a vivid reminder of the dynamic and ever-changing nature of the cosmos. It highlights the powerful forces at play in the universe and the intricate processes that shape the galaxies we observe. As we continue to study these colliding galaxies, we gain deeper insights into the mechanisms of galactic evolution and the role that cannibalism plays in the life cycle of galaxies. With this understanding of galactic cannibalism, we can better appreciate the complex and dynamic nature of the Antennae Galaxies. This process not only contributes to their strange and fascinating features, but also offers a glimpse into the broader processes that drive the evolution of galaxies across the universe. Now, shifting our focus to one of the most explosive phenomena in the cosmos, let's explore the mysterious gamma-ray bursts originating from the Antennae Galaxies. These bursts are among the most energetic events in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. But what exactly causes these intense flashes of gamma rays, and why are they so significant in the context of the Antennae Galaxies? Gamma-ray bursts are thought to occur when massive stars collapse at the end of their lives, forming black holes or neutron stars. In the chaotic environment of the Antennae Galaxies, where star formation is rampant and collisions are frequent, the conditions are ripe for such cataclysmic events. The collision of the two galaxies has created a hotbed of activity, with massive stars forming and dying at an accelerated rate. When these stars exhaust their nuclear fuel, they collapse under their own gravity, triggering a gamma-ray burst that can be observed across vast distances. Another potential cause of gamma-ray bursts in the Antennae Galaxies is the merger of neutron stars. These incredibly dense remnants of dead stars can spiral toward each other, eventually colliding and releasing a tremendous amount of energy in the form of gamma rays. The Antennae Galaxies, with their high density of stars and frequent interactions, provide the perfect environment for such mergers to occur. These events not only produce gamma-ray bursts but also contribute to the creation of heavy elements like gold and platinum, which are scattered into space during the collision. The gamma-ray bursts observed in the Antennae Galaxies are not just spectacular displays of cosmic power. They also offer valuable insights into the processes shaping these galaxies. By studying these bursts, astronomers can learn more about the life cycles of massive stars, the formation of black holes and neutron stars, and the distribution of heavy elements in the universe. Each burst acts as a cosmic beacon, illuminating the conditions within the galaxies and helping scientists piece together the complex history of their evolution. What makes these bursts even more intriguing is their rarity. While gamma-ray bursts are relatively common in the universe, detecting them in a specific galaxy like the Antennae pair is a rare opportunity. The bursts provide a unique window into the extreme environments of colliding galaxies, where the forces of gravity and radiation are pushed to their limits. By analyzing the light and energy from these bursts, researchers can uncover clues about the structure and dynamics of the Antennae Galaxies, as well as the broader processes driving galactic evolution. As we continue to study these powerful events, we gain a deeper understanding of the forces at work in the Antennae Galaxies. Gamma-ray bursts are not just fleeting flashes of light. They are key to unraveling the mysteries of these colliding galaxies and the universe as a whole. With each burst, we move closer to understanding the intricate dance of stars, gas, and gravity that shapes the cosmos. Now, let's turn our attention to another fascinating aspect of the Antennae Galaxies, the twisted and chaotic magnetic fields that weave through these colliding galaxies. Magnetic fields might not be something we can see directly, but their influence is profound, shaping the behavior of gas, dust, and even the birth of new stars. In the Antennae Galaxies, these fields are anything but orderly. They are tangled, turbulent, and full of surprises. The collision of the two galaxies has not only stirred up stars and gas, but also twisted their magnetic fields into a chaotic web. As the galaxies merge, their magnetic fields interact, creating regions where the fields are amplified, twisted, or even torn apart. This chaotic environment has a direct impact on star formation. Magnetic fields can either help or hinder the collapse of gas clouds into new stars. In some areas, the fields provide support, preventing gas from collapsing too quickly. In others, they channel gas into dense streams, accelerating the birth of stars. The result is a patchwork of star-forming regions, each influenced by the local magnetic environment. But the effects of these magnetic fields don't stop at star formation. They also play a crucial role in shaping cosmic radiation. Charged particles like electrons and protons spiral along magnetic field lines, emitting radiation as they move. In the Antennae Galaxies, the twisted fields act like cosmic accelerators, speeding up these particles to incredible energies. This process produces a variety of radiation, from radio waves to X-rays, giving astronomers a unique way to map the invisible magnetic structures within the galaxies. What makes these magnetic fields even more intriguing is their connection to the galaxy's overall evolution. As the Antennae Galaxies continue to merge, their magnetic fields will evolve, influencing everything from the distribution of gas to the formation of new star clusters. By studying these fields, scientists can gain insights into how magnetic forces shape galaxies over time, not just in the antennae pair but across the universe. The chaotic magnetic fields of the Antennae Galaxies are a reminder that even the invisible forces of the cosmos play a vital role in shaping the universe. They are a testament to the complexity of galactic collisions and the intricate interplay of forces that drive the birth and evolution of stars. As we continue to explore these magnetic mysteries, we uncover yet another layer of the Antennae Galaxies' extraordinary story. Now, shifting our gaze to another cosmic enigma, we encounter the ultra-luminous X-ray sources scattered throughout the Antennae Galaxies. These mysterious objects emit staggering amounts of X-ray energy, far exceeding what typical stars or even black holes produce. Their brightness is so intense that they outshine entire star clusters, making them some of the most luminous objects in the X-ray universe. But what exactly are these ultra-luminous X-ray sources, and why do they shine so brightly? The answer lies in a cosmic puzzle that astronomers are still working to solve. One leading theory suggests that these sources could be intermediate mass black holes, larger than stellar black holes but smaller than the supermassive ones at the centers of galaxies. These intermediate black holes would have the gravitational pull needed to attract vast amounts of gas and dust, heating it to extreme temperatures and causing it to emit X-rays. Another possibility is that these sources are stellar mass black holes or neutron stars feeding on material from a companion star at an unusually high rate. In this scenario, the intense X-ray emissions come from the rapid consumption of matter, creating a glowing accretion disk around the compact object. However, the Antennae Galaxies add another layer of complexity to this mystery. The collision and merger of the two galaxies have created an environment rich in gas and dust, providing ample fuel for these X-ray sources. The chaotic interactions between stars, black holes, and gas clouds could be triggering the formation of these ultra-luminous objects, making the Antennae Galaxies a hotspot for their discovery. Yet, despite their brightness, pinpointing their exact nature remains a challenge. Some sources appear to flicker or vary in brightness, hinting at dynamic processes at work, while others remain steady, suggesting a more stable feeding mechanism. What makes these ultra-luminous X-ray sources even more fascinating is their potential to reveal new insights into the life cycles of black holes and neutron stars. By studying their behavior, astronomers can learn more about how these objects form, grow, and interact with their surroundings. They also provide a unique window into the extreme physics of accretion, where matter spirals into a black hole or neutron star, releasing immense amounts of energy in the process. As we continue to explore the Antennae Galaxies, these ultra-luminous X-ray sources stand as a testament to the dynamic and ever-changing nature of the cosmos. They remind us that even in the chaos of colliding galaxies, there are hidden treasures waiting to be uncovered, each with a story to tell about the forces that shape our universe. Now, let's turn our attention to another extraordinary feature of the Antennae Galaxies' galactic winds. These are not the gentle breezes we experience on Earth. but rather colossal streams of gas and particles racing through space at incredible speeds. These winds are so powerful that they can reshape entire regions of a galaxy, and in the Antennae Galaxies, they play a crucial role in the ongoing drama of cosmic evolution. Galactic winds are born from the intense activity within the galaxies, particularly in regions where stars are forming at an explosive rate. As massive stars are born, they burn through their fuel quickly and end their lives in spectacular supernova explosions. These explosions release enormous amounts of energy, heating the surrounding gas and propelling it outward at high velocities. This process creates the winds that sweep through the galaxies, carrying with them not just gas, but also heavy elements forged in the hearts of stars. In the Antennae Galaxies, the collision between the two galaxies has amplified this phenomenon. The chaotic gravitational interactions have triggered bursts of star formation, leading to an even greater number of supernovae. As a result, the galactic winds here are particularly intense, reaching speeds of hundreds of kilometers per second. These winds can stretch across thousands of light years, carving out vast cavities in the interstellar medium and redistributing material throughout the galaxies. But what makes these winds so significant? For one, they act as a cosmic recycling system. The material ejected by the winds doesn't just disappear into space, it eventually cools and falls back into the galaxies, providing the raw ingredients for new stars and planets. This process helps regulate the rate of star formation, ensuring that the galaxies don't exhaust their gas supply too quickly. Additionally, the winds carry heavy elements like carbon, oxygen, and iron into the intergalactic medium, enriching it and paving the way for future generations of stars and planets. The impact of these winds extends beyond the galaxies themselves. As they blow outward, they can collide with gas clouds in the surrounding environment, triggering new waves of star formation. This interaction creates a feedback loop where the winds both suppress and stimulate star formation, depending on the conditions. It's a delicate balance, one that shapes the evolution of the Antennae Galaxies and influences their ultimate fate. Studying galactic winds in the Antennae Galaxies offers astronomers a unique opportunity to understand how these powerful forces operate in extreme environments. By observing the movement of gas and the distribution of elements, scientists can piece together the complex interplay between star formation, supernova, and the interstellar medium. These insights not only shed light on the Antennae Galaxies, but also help us understand similar processes in other galaxies across the universe. As we continue to explore the Antennae Galaxies, the story of galactic winds reminds us of the dynamic and interconnected nature of the cosmos. These winds are more than just a byproduct of stellar activity. They are a driving force in the life cycle of galaxies, shaping their past, present, and future. And in the swirling chaos of the Antennae Galaxies, they are yet another example of the extraordinary phenomena that make this cosmic collision so fascinating to study. Now, let's shift our gaze to another fascinating aspect of the Antennae Galaxies star clusters in chaos. Unlike the orderly star clusters found in more tranquil galaxies, the ones here are born from the fiery turmoil of galactic collision. These clusters are not just collections of stars, they are dynamic, ever-changing systems that reflect the intense environment in which they form. In the Antennae Galaxies, the collision between the two galaxies has created a perfect storm for star cluster formation. The gravitational forces at play compress vast clouds of gas and dust, triggering the birth of thousands of stars at once. These newborn stars often form in dense, tightly packed groups, creating star clusters that are far more massive and chaotic than those found in common galaxies. Some of these clusters contain hundreds of thousands of stars, packed into regions just a few light years across. What makes these clusters truly unique is their chaotic nature. In more stable galaxies, star clusters tend to form in relatively calm environments, allowing them to evolve slowly over billions of years. But in the Antennae Galaxies, the constant gravitational tug of war between the two colliding galaxies disrupts these clusters, pulling them apart or merging them with others. This results in clusters that are constantly reshaping themselves, with stars being flung out or drawn in by the chaotic forces at play. The chaotic environment also affects the lifespan of these clusters. In common galaxies, star clusters can survive for billions of years, gradually losing stars to the surrounding galaxy. But in the Antennae Galaxies, many clusters are short-lived, torn apart by the intense gravitational forces or destroyed by the frequent supernova explosions that occur in such active star-forming regions. This means that the clusters we see today may look very different in just a few million years or even disappear entirely. Despite their chaotic nature, these star clusters play a crucial role in the evolution of the Antennae Galaxies. They act as cosmic nurseries, producing new generations of stars that will eventually spread out and populate the galaxies. The heavy elements forged in the hearts of these stars are also released into the surrounding environment, enriching the gas and dust that will form future stars and planets. Studying these chaotic star clusters gives astronomers a unique window into the processes that shape galaxies during collisions. By observing how these clusters form, evolve, and dissolve, scientists can better understand the forces at work in the Antennae Galaxies and how they compare to those in other merging galaxies. It's a reminder that even in the chaos of a galactic collision, there is a delicate balance between creation and destruction, shaping the galaxies we see today and those that will exist in the future. As we continue to explore the Antennae Galaxies, the story of these chaotic star clusters adds another layer to our understanding of this cosmic collision. They are not just remnants of the past but active participants in the ongoing drama of galactic evolution, showcasing the incredible complexity and beauty of the universe. Now, let's turn our attention to another remarkable feature of the Antennae Galaxies, the vast intergalactic gas bridges that stretch between the two colliding galaxies. These enormous structures, composed primarily of hydrogen gas, act as cosmic highways, transporting material from one galaxy to the other and playing a crucial role in the ongoing drama of star formation. As the two galaxies collide, their gravitational forces pull and stretch the gas between them, creating these massive bridges that can span tens of thousands of light years. These gas bridges are not just remnants of the collision, they are dynamic, active regions where new stars are born. The gas within these bridges is compressed and heated by the gravitational forces, triggering the formation of stars in regions that might otherwise remain dormant. One of the most fascinating aspects of these gas bridges is their ability to fuel star formation in both galaxies. As gas flows along these bridges, it accumulates in dense pockets, creating the perfect conditions for new stars to ignite. This process is particularly intense in the Antennae Galaxies, where the collision has already created a highly active star-forming environment. The gas bridges act as a kind of cosmic pipeline, ensuring that both galaxies continue to receive the raw materials needed for star formation even as they merge. The role of these gas bridges extends beyond just star formation. They also help redistribute heavy elements such as carbon, oxygen, and iron, which are forged in the hearts of stars and released into space during supernova explosions. As these elements travel along the gas bridges, they enrich the interstellar medium, providing the building blocks for future generations of stars and planets. This process is essential for the long-term evolution of the galaxies, as it ensures that the material needed for star formation is continuously replenished. Studying these intergalactic gas bridges gives astronomers valuable insights into the processes that drive galaxy evolution during collisions. By observing how gas flows between the two galaxies, scientists can better understand how mergers shape the structure and composition of galaxies over time. These bridges also provide a unique opportunity to study the conditions under which stars form in extreme environments, offering clues about the early universe when galaxy collisions were much more common. The intergalactic gas bridges in the Antennae Galaxies are a testament to the incredible complexity of galactic collisions. They remind us that even in the chaos of such events, there is a delicate balance between destruction and creation, as the forces of gravity and motion work together to shape the future of these galaxies. As we continue to explore the Antennae Galaxies, these gas bridges offer yet another glimpse into the dynamic and ever-changing nature of the universe. Now, let's shift our focus to a phenomenon that takes us into the realm of high-energy physics: cosmic ray acceleration in the Antennae Galaxies. These galaxies are not just a spectacle of colliding stars and swirling gas. They are also natural particle accelerators, capable of propelling cosmic rays to astonishing speeds. But what exactly are cosmic rays, and how do the Antennae Galaxies play a role in their acceleration? Cosmic rays are high-energy particles, primarily protons and atomic nuclei, that travel through space at nearly the speed of light. While their origins have long puzzled scientists, the Antennae Galaxies provide a unique laboratory for studying how these particles are accelerated to such extreme energies. The chaotic environment of the colliding galaxies, with their intense gravitational forces and magnetic fields, creates the perfect conditions for cosmic ray acceleration. One of the key mechanisms at play here is shock acceleration. As the two galaxies collide, they generate massive shock waves that ripple through the interstellar medium. These shock waves act like cosmic catapults, accelerating particles to incredible speeds. When particles encounter these shock fronts, they gain energy with each pass, much like a surfer catching a wave. Over time, this process can propel particles to energies millions of times greater than those produced in human-made particle accelerators. But the story doesn't end there. The supermassive black holes at the cores of the Antennae Galaxies also contribute to this cosmic particle acceleration. As matter spirals into these black holes, it forms powerful jets that shoot out into space at nearly the speed of light. These jets are not only spectacular to observe but also serve as another source of cosmic ray acceleration. The intense magnetic fields surrounding the jets can further boost the energy of particles, sending them hurtling across the universe. The implications of this phenomenon are profound. Cosmic rays play a crucial role in shaping the interstellar medium, influencing star formation and even affecting the chemistry of galaxies. By studying how the Antennae Galaxies accelerate these particles, scientists can gain insights into the fundamental processes that govern the universe. This research also has practical applications, helping us understand the effects of cosmic rays on space travel and the potential hazards they pose to astronauts. What makes the Antennae Galaxies particularly fascinating is their ability to accelerate cosmic rays on such a massive scale. The collision between the two galaxies creates a dynamic environment where multiple acceleration mechanisms work in tandem, producing some of the most energetic particles in the universe. This makes the Antennae Galaxies a key target for astronomers and physicists alike, as they seek to unravel the mysteries of cosmic ray origins and their impact on the cosmos. As we continue to explore the Antennae Galaxies, the study of cosmic ray acceleration offers yet another window into the complex interplay of forces that shape our universe. From shock waves to black hole jets, these galaxies remind us that even in the chaos of a collision, there is a delicate balance of creation and destruction, driving the evolution of the cosmos in ways we are only beginning to understand. Now, let's turn our attention to a phenomenon that illuminates the hidden corners of the Antennae Galaxies: their intense infrared glow. While much of the light from these colliding galaxies is visible to the human eye, a significant portion of their energy is emitted in the form of infrared radiation. This glow, invisible to us without specialized instruments, holds the key to uncovering some of the most active and obscured regions of star formation within the galaxies. The infrared glow of the Antennae Galaxies is primarily caused by the vast amounts of cosmic dust present in their swirling arms and tidal tails. As stars form, they heat up the surrounding dust, which then radiates this energy as infrared light. Because dust absorbs visible light, many of these star-forming regions are hidden from traditional optical telescopes. However, infrared telescopes can peer through this dust, revealing the intense activity happening beneath the surface. What makes this infrared glow so fascinating is its connection to the galaxy's collision. The gravitational forces at play during the merger compress gas and dust, triggering bursts of star formation. These newly formed stars, often embedded in thick clouds of dust, emit infrared light as they heat their surroundings. This means that the brighter the infrared glow, the more active the star-forming regions are. In the Antennae Galaxies, this glow is particularly intense, indicating an extraordinary rate of star birth. But the story doesn't stop there. The infrared glow also provides clues about the life cycle of stars and the evolution of galaxies. By studying the distribution and intensity of this radiation, astronomers can map out where stars are forming and how these regions change over time. This helps scientists understand how galactic collisions, like the one shaping the Antennae Galaxies, influence the birth and death of stars on a cosmic scale. One of the most intriguing aspects of this phenomenon is how it reveals the hidden structure of the galaxies. Infrared observations have uncovered massive star clusters and supernova remnants that are completely obscured in visible light. These discoveries highlight the importance of looking beyond what our eyes can see to fully grasp the complexity of the universe. The Antennae Galaxies' infrared glow is more than just a byproduct of their collision. It's a window into the hidden processes driving their evolution. From the birth of new stars to the recycling of cosmic material, this phenomenon offers a unique perspective on the dynamic nature of these galaxies. As we continue to explore the universe in different wavelengths of light, the infrared glow of the Antennae Galaxies reminds us that there is always more to discover, even in the most familiar corners of the cosmos. Now, let's shift our gaze to a phenomenon that bends the very fabric of space and light: gravitational lensing. In the Antennae Galaxies, the immense gravitational pull of their massive structures, including supermassive black holes and dense star clusters, warps the surrounding space-time. This distortion acts like a cosmic magnifying glass, bending and amplifying light from objects behind them, a phenomenon known as gravitational lensing. Gravitational lensing occurs when the gravity of a massive object, like a galaxy or black hole, curves the path of light traveling from a more distant object. In the case of the Antennae Galaxies, this effect can create stunning visual distortions, such as arcs, rings, or even multiple images of the same background object. These lensing effects not only provide a breathtaking cosmic spectacle, but also serve as powerful tools for astronomers. One of the most remarkable aspects of gravitational lensing in the Antennae Galaxies is its ability to reveal objects that would otherwise be too faint or distant to observe. By magnifying the light from background galaxies, lensing allows scientists to study the early universe in unprecedented detail. This includes observing some of the first galaxies that formed after the Big Bang, offering a glimpse into the origins of cosmic structures. But the lensing effects in the Antennae Galaxies aren't just about magnification, they also help astronomers map the distribution of dark matter. Since dark matter doesn't emit light, its presence can only be inferred through its gravitational effects. By analyzing how light bends around the galaxies, researchers can create detailed maps of the invisible dark matter that permeates the Antennae Galaxies, shedding light on its role in shaping the universe. Another fascinating aspect of gravitational lensing in these galaxies is its connection to their ongoing collision. The chaotic gravitational forces at play during the merger amplify the lensing effects, creating even more dramatic distortions. This makes the Antennae Galaxies a unique laboratory for studying how gravitational lensing behaves in extreme environments, providing insights into the nature of gravity itself. Gravitational lensing in the Antennae Galaxies is a testament to the power of gravity to shape not just the galaxies themselves, but also our understanding of the cosmos. From revealing hidden galaxies to mapping dark matter, this phenomenon opens a window into the unseen forces that govern the universe. As we continue to explore the Antennae Galaxies, gravitational lensing reminds us that even the most familiar objects in the sky can hold secrets waiting to be uncovered. Now, let's turn our attention to a phenomenon that reveals the hidden chemistry of the cosmos, the unusual chemical composition of the Antennae Galaxies. Unlike many other galaxies, the Antennae Galaxies boast a unique blend of elements that set them apart, offering clues about their violent history and the processes shaping their evolution. One of the most striking features of the Antennae Galaxies is their abundance of heavy elements such as iron, oxygen, and carbon. These elements are forged in the hearts of stars and scattered into space through supernova explosions and stellar winds. However, the Antennae Galaxies contain higher concentrations of these elements compared to other galaxies, a result of their intense star-forming activity and frequent supernova. This chemical richness makes them a treasure trove for astronomers studying the life cycles of stars and the dispersal of elements across the universe. But it's not just the presence of these heavy elements that makes the Antennae Galaxies unique, it's also the unusual ratios in which they appear. For instance, certain regions within the galaxies show elevated levels of nitrogen and neon, elements typically produced in massive stars that end their lives in spectacular explosions. These anomalies suggest that the Antennae Galaxies have experienced multiple waves of star formation, each leaving behind a distinct chemical fingerprint. Another intriguing aspect of their chemical makeup is the presence of rare elements like lithium and beryllium. These lightweight elements are often destroyed in the intense environments of stars, making their detection in the Antennae Galaxies particularly surprising. Their presence hints at processes that might preserve or even produce these elements, challenging our understanding of stellar and galactic evolution. The collision between the two galaxies plays a significant role in shaping their chemical composition. As the galaxies merge, shock waves ripple through their gas clouds, triggering bursts of star formation and enriching the interstellar medium with newly synthesized elements. This chaotic environment creates a cosmic laboratory where astronomers can study how chemical elements are distributed and recycled in extreme conditions. The unusual chemical composition of the Antennae Galaxies not only sheds light on their own history, but also provides insights into the broader processes that govern galaxy evolution. By analyzing the elements present in these galaxies, scientists can piece together the story of how galaxies grow, change, and interact over billions of years. As we continue to explore the Antennae Galaxies, their chemical makeup serves as a reminder that the universe is not only vast and mysterious but also rich with diversity. Each element tells a story, and in the Antennae Galaxies, those stories are written in the language of stars, explosions, and cosmic collisions. Now, let's shift our focus to a phenomenon that showcases the raw power of cosmic collisions, the galactic shock waves rippling through the Antennae Galaxies. These shock waves are like cosmic tsunamis created by the immense gravitational forces unleashed as the two galaxies collide and merge. They ripple through the interstellar medium, compressing gas clouds and triggering dramatic changes in the galaxy's structure and behavior. As the shock waves travel through the Antennae Galaxies, they compress vast clouds of gas and dust, creating regions of intense pressure. These compressed regions become the birthplaces of new stars, as the increased density allows gravity to pull the material together, igniting the process of star formation. This is why the Antennae Galaxies are such a hotspot for star birth. Their collision has turned them into a cosmic factory, churning out stars at an astonishing rate. But the effects of these shock waves go beyond just creating new stars. They also heat the surrounding gas to incredibly high temperatures, causing it to glow brightly in X-rays and other forms of high-energy radiation. This heated gas can be observed by telescopes, providing astronomers with a vivid picture of the shock waves' impact on the galaxies. The shock waves also stir up the interstellar medium, mixing elements forged in stars and spreading them throughout the galaxies, enriching the material available for future star formation. Interestingly, these shock waves don't just move in straight lines. The chaotic nature of the collision causes them to twist and bend, creating complex patterns that ripple through the galaxies. These patterns can be seen in the intricate structures of the Antennae Galaxies, such as their long tidal tails and swirling gas clouds. The shock waves also contribute to the galaxy's overall turbulence, making their environment far more dynamic and unpredictable than that of calmer, more isolated galaxies. The presence of these shock waves also has long-term implications for the Antennae Galaxies. As they continue to ripple through the galaxies, they will shape their evolution, influencing where and how stars form and how the galaxy's structure changes over time. By studying these shock waves, astronomers can gain insights into the processes that drive galaxy evolution, not just in the Antennae Galaxies but across the universe. In many ways, the galactic shock waves in the Antennae Galaxies are a testament to the transformative power of cosmic collisions. They remind us that even in the vastness of space, the forces at play can create breathtaking beauty and complexity, shaping the universe in ways we are only beginning to understand. Now, let's turn our attention to one of the most striking features of the Antennae Galaxies, their classification as starburst galaxies. But what exactly does that mean, and why are the Antennae Galaxies such a standout example? Starburst galaxies are galaxies that experience an exceptionally high rate of star formation, far exceeding what we see in typical galaxies. The Antennae Galaxies, with their collision-driven chaos, are a textbook case of this phenomenon. The collision between the two galaxies has created the perfect conditions for a starburst. As the galaxies merge, their gravitational forces compress vast clouds of gas and dust, triggering an explosion of star formation. In fact, the Antennae Galaxies are producing stars at a rate hundreds of times faster than our own Milky Way. This intense activity has earned them the title of starburst galaxies, and it's one of the reasons they're so fascinating to astronomers. What makes the Antennae Galaxies unique is not just the sheer number of stars being born, but also the way this star formation is distributed. Unlike in calmer galaxies, where star formation tends to occur in specific regions, the Antennae Galaxies are alive with activity across their entire structure. From their long tidal tails to their chaotic cores, new stars are igniting everywhere, creating a dazzling display of cosmic fireworks. This widespread star formation is fueled by the collision itself. As the galaxies interact, shock waves ripple through their gas clouds, compressing them and triggering the birth of new stars. These shock waves, combined with the gravitational forces at play, create a highly turbulent environment where star formation can occur on a massive scale. The result is a galaxy that's not just forming stars, but doing so in a way that's both intense and widespread. Another unique aspect of the Antennae Galaxies is the sheer variety of stars being formed. From massive, short-lived stars that burn brightly and die young, to smaller, longer-lived stars that will shine for billions of years, the Antennae Galaxies are a melting pot of stellar diversity. This variety provides astronomers with a unique opportunity to study different stages of star formation and evolution, all within a single galaxy. The starburst activity in the Antennae Galaxies also has a profound impact on their surroundings. The intense radiation from newly formed stars heats the surrounding gas, causing it to glow brightly in various wavelengths of light. This makes the Antennae Galaxies a treasure trove of data for astronomers who can study the interplay between star formation, radiation, and the interstellar medium. In many ways, the Antennae Galaxies are a living laboratory for understanding starburst galaxies. Their collision-driven star formation offers a glimpse into the processes that shape galaxies and drive their evolution. By studying the Antennae Galaxies, astronomers can gain insights into how starbursts occur, what triggers them, and how they influence the future of the galaxies involved. It's a reminder that even in the vastness of space, the forces at play can create extraordinary phenomena that challenge our understanding of the universe. Now, let's shift our focus to another fascinating aspect of the Antennae Galaxies: cosmic recycling. This process is a remarkable example of how the universe reuses its resources, turning the remnants of dying stars into the building blocks for new ones. In the Antennae Galaxies, this cycle of creation and destruction is happening on an extraordinary scale. When massive stars reach the end of their lives, they don't simply fade away. Instead, they explode in spectacular supernova, scattering their material across space. This material, rich in heavy elements like carbon, oxygen, and iron, mixes with the surrounding gas and dust. Over time, these enriched clouds of material are drawn together by gravity, forming the seeds of new stars and planets. This is the essence of cosmic recycling, and the Antennae Galaxies are a prime example of this process in action. What makes the Antennae Galaxies particularly interesting is the sheer volume of material being recycled. The collision between the two galaxies has created a chaotic environment where supernovae are frequent, and the resulting debris is spread far and wide. This means that the galaxies are not just forming new stars, they're doing so using material that has already been part of previous generations of stars. It's a cosmic version of reusing and repurposing, and it plays a crucial role in the evolution of galaxies. This recycling process also has a profound impact on the chemical composition of the Antennae Galaxies. Each generation of stars enriches the interstellar medium with heavier elements, which are then incorporated into the next generation of stars and planets. Over time, this leads to a gradual increase in the abundance of elements like silicon, magnesium, and iron elements that are essential for the formation of rocky planets like Earth. In this way, the Antennae Galaxies are not just recycling material, they're also building the ingredients for future worlds. Another fascinating aspect of cosmic recycling in the Antennae Galaxies is the role of stellar winds. As stars age, they often expel material into space through powerful winds. This material, too, becomes part of the recycling process, mixing with the gas and dust in the galaxies and contributing to the formation of new stars. In the Antennae Galaxies, where star formation is already happening at an incredible rate, these stellar winds add another layer of complexity to the recycling process. The result is a galaxy that's constantly renewing itself, using the remnants of its past to build its future. This cycle of creation and destruction is a fundamental aspect of how galaxies evolve, and the Antennae Galaxies provide a unique opportunity to study this process in detail. By observing how material is recycled in these galaxies, astronomers can gain insights into the life cycles of stars, the formation of planets, and the evolution of galaxies over billions of years. In many ways, the Antennae Galaxies are a testament to the resilience and creativity of the universe. They show us that even in the face of destruction, there is always the potential for new beginnings. Through cosmic recycling, the Antennae Galaxies are not just surviving, they're thriving, creating new stars, planets, and possibilities in a never-ending cycle of renewal. Now, let's turn our attention to one of the most dramatic phenomena in the Antennae Galaxies: black hole jets. These jets are streams of high-energy particles that are ejected at nearly the speed of light from the regions surrounding the supermassive black holes at the cores of the galaxies. These jets are not just spectacular to observe, they play a crucial role in shaping the environment around them, influencing everything from star formation to the distribution of gas and dust. The supermassive black holes in the Antennae Galaxies are incredibly active, and as they consume matter, they don't just pull material in, they also shoot some of it back out into space. This happens because not all the material falling toward the black hole makes it past the event horizon. Instead, some of it gets funneled into powerful magnetic fields and accelerated outward in the form of jets. These jets can stretch for thousands of light years, extending far beyond the galaxies themselves. What makes these jets so fascinating is their sheer power. The particles in the jets are accelerated to such high speeds that they emit intense radiation across the electromagnetic spectrum, from radio waves to X-rays. This makes the jets visible to astronomers using a variety of telescopes, allowing us to study their structure and behavior in detail. In the Antennae Galaxies, the jets are particularly striking because of the chaotic environment created by the ongoing collision between the two galaxies. This collision has stirred up the gas and dust, creating the perfect conditions for the black holes to produce these spectacular jets. But the impact of these jets goes far beyond their visual appeal. They have a profound effect on the surrounding space. As the jets travel through the galaxies, they interact with the interstellar medium, heating the gas and pushing it around. This can trigger or suppress star formation depending on the circumstances. In some cases, the jets compress gas clouds, causing them to collapse and form new stars. In other cases, they blow the gas away, preventing stars from forming altogether. This dual role makes black hole jets a key factor in the evolution of galaxies. Another intriguing aspect of these jets is their ability to transport energy and matter over vast distances. The particles in the jets carry energy from the black hole out into the intergalactic medium, where they can influence the growth of other galaxies and even the large-scale structure of the universe. In the Antennae Galaxies, this process is amplified by the collision, which has already created a turbulent and dynamic environment. The jets add another layer of complexity to this already chaotic system, making the Antennae Galaxies a unique laboratory for studying the effects of black hole activity. One of the most remarkable things about black hole jets is how they reveal the interconnectedness of cosmic phenomena. The jets are a direct result of the black hole's feeding process, which in turn is influenced by the collision between the galaxies. This collision has created a feedback loop where the black holes shape their surroundings, and those surroundings influence the black holes. It's a dynamic and ever-changing system, and studying it helps us understand how black holes and galaxies evolve together over time. In the Antennae Galaxies, black hole jets are more than just a cosmic spectacle. They're a driving force behind the galaxy's evolution. By studying these jets, astronomers can gain insights into the behavior of supermassive black holes, the processes that shape galaxies, and the complex interplay between different cosmic phenomena. It's a reminder that even the most extreme events in the universe are part of a larger, interconnected story, one that continues to unfold in the Antennae Galaxies. Now, shifting our focus to another fascinating aspect of the Antennae Galaxies, let's explore the evidence of galactic cannibalism, a process where these colossal galaxies consume smaller ones. This phenomenon isn't just a dramatic cosmic event. It's a key factor in shaping the structure and evolution of the Antennae Galaxies. One of the most compelling pieces of evidence for galactic cannibalism lies in the observation of disrupted dwarf galaxies in the vicinity of the antennae. Astronomers have detected streams of stars and gas that appear to have been torn away from smaller galaxies, now being absorbed into the larger structures of the antennae. These streams, often referred to as tidal debris, are telltale signs of gravitational interactions, where the immense pull of the Antennae Galaxies has stripped material from their smaller neighbors. Another clue comes from the unusual distribution of stars within the Antennae Galaxies themselves. In regions where galactic cannibalism is thought to have occurred, astronomers have found star clusters with distinct chemical compositions that differ from the rest of the galaxy. These clusters are believed to be remnants of the smaller galaxies that were consumed, their stars now integrated into the larger galactic structure. This mixing of stellar populations provides a clear record of past mergers and acquisitions. the process of galactic cannibalism also leaves its mark on the overall shape of the Antennae Galaxies. As smaller galaxies are pulled in and absorbed, their material contributes to the chaotic, irregular structure we see today. The tidal tails, those long, sweeping arcs of gas and stars stretching across space, are a direct result of these interactions. They serve as a cosmic fingerprint, revealing the history of collisions and mergers that have shaped the galaxies over billions of years. But galactic cannibalism isn't just about destruction, it's also a creative force. The influx of fresh gas and stars from consumed galaxies can trigger bursts of star formation, adding new layers of complexity to the Antennae Galaxies. This process helps explain why these galaxies are so rich in young, massive stars and why their star-forming regions are so intense. In a way, galactic cannibalism is a form of cosmic recycling, where the material from smaller galaxies is repurposed to fuel the growth and evolution of larger ones. By studying the evidence of galactic cannibalism in the Antennae Galaxies, astronomers gain valuable insights into how galaxies grow and change over time. It's a reminder that even the largest structures in the universe are shaped by the interactions and mergers of smaller ones. This process not only shapes the physical structure of galaxies but also influences their chemical makeup, star formation rates, and overall evolution. In the Antennae Galaxies, the story of galactic cannibalism is written in the stars, gas, and dust, a testament to the dynamic and ever-changing nature of the cosmos. Now, let's turn our attention to one of the most dynamic aspects of the Antennae Galaxies, the triggers behind their intense star formation. Unlike many other galaxies where star formation occurs at a more gradual pace, the Antennae Galaxies are a hotbed of stellar activity, producing stars at a rate that far exceeds the norm. But what exactly sets off this cosmic fireworks display? The primary driver of this explosive star formation is the ongoing collision between the two galaxies. As they merge, their gravitational forces compress vast clouds of gas and dust, creating the perfect conditions for new stars to ignite. These collisions generate shock waves that ripple through the interstellar medium, compressing gas to such high densities that it collapses under its own gravity, forming new stars. This process is so intense that it can produce entire star clusters in a relatively short period of time, compared to the more sedate star formation seen in isolated galaxies. Another key trigger is the influx of fresh material from smaller galaxies consumed through galactic cannibalism. As we discussed earlier, the Antennae Galaxies are known for absorbing smaller neighbors, and this process brings in new gas and dust that fuels star formation. This material not only increases the overall mass available for star formation, but also introduces turbulence and instability into the galactic environment, further enhancing the conditions needed for stars to form. The chaotic structure of the Antennae Galaxies also plays a significant role. The tidal tails and distorted shapes created by the collision create regions of high pressure and density where star formation is particularly intense. These areas, often referred to as starburst regions, are hotspots of activity, producing some of the brightest and most massive stars in the galaxies. The sheer scale of these regions sets the Antennae Galaxies apart from more stable, spiral galaxies, where star formation tends to be more evenly distributed and less explosive. Interestingly, the star formation triggers in the Antennae Galaxies also differ from those in other merging galaxies. While many colliding galaxies experience bursts of star formation, the Antennae Galaxies stand out due to the sheer intensity and duration of their activity. This is likely due to the specific conditions of their collision, including the angle of impact, the relative masses of the galaxies, and the amount of gas available. These factors combine to create a unique environment where star formation is not just a brief event but an ongoing process that continues to shape the galaxies over time. By studying these triggers, astronomers gain valuable insights into how galaxies evolve and how their environments influence star formation. The Antennae Galaxies serve as a cosmic laboratory, offering a glimpse into the forces that drive one of the most fundamental processes in the universe. As we continue to explore these galaxies, we uncover more about the delicate balance of forces that govern the birth of stars and the evolution of galaxies themselves. Now, let's shift our gaze to one of the most visually stunning phenomena in the Antennae Galaxies, the cosmic fireworks of star formation and supernova explosions. Imagine a celestial light show on a scale so vast it defies comprehension. The Antennae Galaxies are not just forming stars, they are doing so in a way that resembles a grand cosmic celebration, with bursts of light and energy illuminating the darkness of space. At the heart of this spectacle are the regions of intense star formation, where massive clouds of gas and dust collapse under gravity, igniting the birth of new stars. These newborn stars shine with incredible brightness, their light piercing through the surrounding dust and gas. But the fireworks don't stop there. As these massive stars reach the end of their lives, they explode in supernova, releasing energy equivalent to billions of nuclear bombs in a single instant. These explosions send shock waves rippling through the galaxy, compressing nearby gas clouds and triggering even more star formation in a self-perpetuating cycle of creation and destruction. What makes the Antennae Galaxies particularly remarkable is the sheer density of these events. In more stable galaxies, supernova are rare and widely spaced, but here they occur with astonishing frequency. This is due to the galaxy's ongoing collision, which has created an environment ripe for both star formation and stellar death. The result is a dazzling display of light and energy, with supernova explosions lighting up the galactic landscape like fireworks on a cosmic scale. These cosmic fireworks are not just beautiful to observe, they also play a crucial role in shaping the galaxies. The energy released by supernova enriches the surrounding space with heavy elements like iron, gold, and uranium, which are essential for the formation of planets and ultimately life. At the same time, the shock waves from these explosions compress gas clouds, triggering the birth of new stars and perpetuating the cycle of stellar evolution. The Antennae Galaxies offer us a front-row seat to this extraordinary process, allowing astronomers to study the intricate relationship between star formation and supernova explosions. By observing these cosmic fireworks, we gain a deeper understanding of how galaxies evolve and how the elements necessary for life are forged in the hearts of dying stars. It's a reminder that even in the vastness of space, destruction and creation are intimately linked, shaping the universe in ways that continue to inspire awe and wonder. Now, let's turn our attention to another fascinating feature of the Antennae Galaxies, the massive interstellar gas clouds that play a pivotal role in the galaxy's ongoing drama of star formation. These clouds, composed primarily of hydrogen and helium, are the raw materials from which stars are born. Stretching across vast regions of space, they serve as the cosmic nurseries where gravity works its magic, pulling gas and dust together to ignite the birth of new stars. What makes these interstellar gas clouds in the Antennae Galaxies so extraordinary is their sheer size and density. Unlike the more diffuse clouds found in common galaxies, the gas clouds here are compressed and agitated by the ongoing collision between the two galaxies. This compression creates regions of intense pressure and temperature, providing the perfect conditions for star formation. As these clouds collapse under their own gravity, they fragment into smaller clumps, each of which can give rise to dozens or even hundreds of new stars. But the story doesn't end there. These gas clouds are not just passive reservoirs of material, they are dynamic and ever-changing. The energy from nearby supernova explosions and the radiation from young, massive stars can heat and ionize the gas, creating glowing regions known as nebulae. These nebulae are not only stunning to observe but also play a crucial role in the life cycle of stars. They act as both the birthplace of new stars and the final resting place for the material ejected by dying ones, recycling elements back into the galaxy for future generations of stars and planets. The interstellar gas clouds in the Antennae Galaxies also serve as a laboratory for astronomers studying the processes of star formation. By observing how these clouds collapse, fragment, and ignite, scientists can piece together the intricate steps involved in the birth of stars. This research is particularly valuable because the Antennae Galaxies offer a unique environment where star formation occurs at an accelerated rate, providing insights that are difficult to obtain in more stable galaxies. In addition to their scientific importance, these gas clouds are a visual spectacle. When viewed through telescopes, they appear as swirling, glowing patches of light, their intricate shapes sculpted by the forces of gravity, radiation, and magnetic fields. They remind us that even in the cold, dark reaches of space, there is beauty and complexity, with every cloud holding the potential for new beginnings. As we continue to explore the Antennae Galaxies, the interstellar gas clouds stand as a testament to the dynamic and ever-changing nature of the universe. They are not just the building blocks of stars, but also the threads that weave together the story of galactic evolution, connecting the past, present, and future in a cosmic dance of creation and transformation. Now, let's take a step back in time to uncover the dramatic history of the Antennae Galaxies and the collision that has shaped their extraordinary form. The story of these galaxies is one of cosmic chaos and transformation, unfolding over hundreds of millions of years. Around 600 million years ago, the two galaxies that would become the Antennae began their fateful approach. At this early stage, they were separate spiral galaxies, each with its own distinct structure and rotation. As they drifted closer, their mutual gravitational pull began to distort their shapes, stretching their outer regions into long, sweeping arcs. This marked the beginning of a slow but inevitable dance that would forever alter their destinies. By approximately 300 million years ago, the galaxies had entered the first phase of their collision. Their outer arms began to intertwine, creating vast tidal tails of gas, dust, and stars that stretched across space. These tails, which give the Antennae Galaxies their distinctive name, are a direct result of the immense gravitational forces at play. During this period, the collision also triggered the first waves of intense star formation, as the compressed gas clouds ignited into brilliant bursts of new stars. Fast forward to about 100 million years ago, and the galaxies had reached the peak of their collision. Their cores, once separated by vast distances, were now drawing closer, creating a maelstrom of activity. The supermassive black holes at the centers of each galaxy began to interact, their gravitational pull warping the surrounding space and accelerating the formation of stars and star clusters. This period saw the birth of some of the most massive and luminous stars in the galaxies, as well as the frequent occurrence of supernova explosions. Today, the Antennae Galaxies are in the final stages of their merger. Their cores are now just tens of thousands of light-years apart, and they are on a trajectory to eventually combine into a single, larger galaxy. The collision has left them with a chaotic, irregular structure marked by swirling clouds of gas, glowing nebulae, and dense clusters of stars. Yet, even as they merge, the galaxies continue to evolve, with new stars forming at an astonishing rate and the remnants of older stars enriching the interstellar medium with heavy elements. This timeline of the galactic collision not only explains the current appearance of the Antennae Galaxies, but also offers a glimpse into the future of our own Milky Way. In about 4 billion years, the Milky Way and the Andromeda Galaxy are expected to undergo a similar collision, reshaping both galaxies in ways that echo the story of the Antennae. As we piece together the history of this cosmic collision, we gain a deeper understanding of the forces that shape galaxies and the dynamic processes that drive their evolution. The Antennae Galaxies stand as a vivid reminder that the universe is a place of constant change, where even the most massive structures are not immune to the pull of gravity and the passage of time. Next, we'll explore how this collision has influenced the distribution of cosmic dust and the role it plays in the ongoing drama of star formation within the Antennae Galaxies. Now, let's turn our attention to one of the most visually striking yet enigmatic features of the Antennae Galaxies, the massive cosmic dust storms that swirl through their chaotic structure. These storms, composed of fine particles of dust and gas, are not just a spectacle to behold, but also play a critical role in shaping the galaxy's evolution and the processes occurring within them. The collision of the two galaxies has created an environment where dust is abundant and constantly in motion. As the galaxy's gravitational forces pull and twist their structures, vast clouds of dust are stirred up, forming storms that stretch across thousands of light years. These storms are so dense that they often obscure the light from stars and other celestial objects, creating regions of darkness that contrast sharply with the bright, glowing nebulae and star clusters around them. But these dust storms are far more than just cosmic curtains. They are active participants in the galaxy's star-forming drama. Within these swirling clouds, dust particles collide and clump together, providing the raw material needed for new stars to form. As the dust compresses under the influence of gravity, it heats up, eventually igniting into the brilliant fires of young stars. This process is particularly intense in the Antennae Galaxies, where the collision has created ideal conditions for such activity. However, the dust storms also present a challenge for astronomers. Their opacity makes it difficult to observe the regions behind them, hiding crucial details about star formation and the distribution of matter within the galaxies. To overcome this, scientists rely on infrared and radio telescopes, which can penetrate the dust and reveal the hidden structures beneath. These observations have shown that the dust storms are not uniform, but instead vary greatly in density and composition, adding another layer of complexity to the galaxy's already intricate makeup. The impact of these dust storms extends beyond star formation. They also influence the temperature and chemistry of the interstellar medium, the vast space between stars. By absorbing and re-emitting light, the dust helps regulate the energy flow within the galaxies, affecting everything from the formation of planets to the behavior of cosmic rays. In this way, the dust storms are not just a byproduct of the collision, but a key player in the ongoing evolution of the Antennae Galaxies. As we continue to study these cosmic dust storms, we gain a deeper appreciation for their role in the grand tapestry of galactic evolution. They remind us that even the smallest particles can have a profound impact on the largest structures in the universe. Next, we'll explore how the movement of star clusters within the Antennae Galaxies adds yet another layer of complexity to their dynamic and ever-changing nature. Now, shifting our focus to another fascinating aspect of the Antennae Galaxies, let's delve into the phenomenon of star cluster migration. Within these colliding galaxies, star clusters are not static entities but dynamic groups that move and evolve over time, driven by the immense gravitational forces at play. This migration is a key factor in shaping the galaxy's structure and the distribution of their stellar populations. As the two galaxies collide and merge, their gravitational interactions create a chaotic environment where star clusters are pulled and pushed in various directions. These clusters, which can contain anywhere from a few hundred to millions of stars, are influenced by the gravitational tug of war between the galaxy's cores, as well as the tidal forces generated by their collision. Over time, this causes the clusters to drift away from their original locations, migrating through the galaxies like cosmic nomads. One of the most intriguing aspects of this migration is how it affects the clusters themselves. As they move through regions of varying density and gravitational influence, some clusters may be stretched or compressed, altering their shape and structure. In extreme cases, clusters can even be torn apart by the intense gravitational forces, scattering their stars across the galaxies. This process, known as tidal disruption, contributes to the galaxy's overall stellar distribution and can lead to the formation of new, smaller clusters or even isolated stars. Interestingly, not all star clusters are equally affected by migration. Dense, tightly bound clusters are more resistant to disruption and can survive longer journeys through the galaxies. In contrast, looser clusters are more vulnerable to the forces acting upon them and may dissolve more quickly. This difference in resilience creates a diverse population of star clusters within the Antennae Galaxies, ranging from ancient, stable clusters to younger, more transient ones. The migration of star clusters also has broader implications for the galaxy's evolution. As clusters move, they interact with the surrounding gas and dust, triggering new waves of star formation or altering the chemistry of the interstellar medium. Additionally, the gravitational influence of migrating clusters can shape the galaxy's overall structure, contributing to the formation of features like tidal tails and bridges. By studying star cluster migration, astronomers gain valuable insights into the complex interplay of forces within colliding galaxies. It highlights how even the smallest structures can have a significant impact on the larger cosmic picture. Next, we'll turn our attention to the intense activity occurring in the cores of the Antennae Galaxies, where supermassive black holes and their surroundings create some of the most energetic phenomena in the universe. Now, let's journey into the heart of the Antennae Galaxies, where the cores of these colliding giants are alive with some of the most extreme activity in the universe. The galactic cores are not just the central hubs of these galaxies, they are powerhouses of energy, home to supermassive black holes and swirling masses of gas and stars that create a cosmic spectacle unlike anything else. At the center of each galaxy lies a supermassive black hole, millions of times more massive than our Sun. These black holes are not dormant, they are actively feeding on the surrounding material, pulling in gas, dust, and even stars. As this material spirals inward, it heats up to incredible temperatures, emitting vast amounts of energy across the electromagnetic spectrum. This process creates some of the brightest and most energetic regions in the Antennae Galaxies, known as active galactic nuclei. The intense activity in the cores doesn't just stay confined to the black holes themselves. The energy released during this feeding process generates powerful jets of particles that shoot out at nearly the speed of light, extending far beyond the galaxy's cores. These jets can stretch for thousands of light years, carving through the surrounding gas and dust and influencing the structure of the galaxies on a massive scale. The jets also heat the interstellar medium, triggering waves of star formation or, in some cases, preventing it by blowing away the gas needed to form new stars. But the core's influence doesn't stop there. The gravitational pull of the supermassive black holes affects the motion of stars and gas in their vicinity, creating chaotic orbits and intense gravitational interactions. This can lead to the formation of dense star clusters near the cores, as well as the ejection of stars at high speeds into the outer regions of the galaxies. These runaway stars can travel vast distances, carrying with them the imprint of the core's immense power. Another fascinating aspect of the galactic cores is their role in the galaxy's collision. As the two galaxies merge, their cores are drawn closer together, setting the stage for a dramatic cosmic dance. Eventually, the supermassive black holes at the centers of each galaxy will likely spiral toward each other, merging into an even larger black hole. This process releases gravitational waves, ripples in space-time, that can be detected across the universe. While this final merger is still millions of years away, the activity in the cores today gives us a glimpse of the incredible forces at work. The intense activity in the cores of the Antennae Galaxies not only shapes their current structure but also influences their future evolution. By studying these regions, astronomers can better understand how supermassive black holes grow, how they interact with their surroundings, and how they contribute to the life cycle of galaxies. Next, we'll explore how the Antennae Galaxies act as natural particle accelerators, producing high-energy particles that reveal even more about the mysteries of the cosmos. Now, let's shift our focus to one of the most extraordinary phenomena in the Antennae Galaxies, their role as cosmic particle accelerators. These colliding galaxies are not just a spectacle of light and energy. They are also natural laboratories for some of the most energetic processes in the universe. Within their chaotic environment, particles are accelerated to incredible speeds, reaching energies that rival those produced by the most advanced human-made particle accelerators on Earth. The key to this phenomenon lies in the intense magnetic fields and shock waves generated by the collision of the two galaxies. As gas and dust are compressed and heated during the merger, they create turbulent regions where particles can be propelled to extreme velocities. These particles, often electrons and protons, are accelerated by the powerful magnetic fields that twist and stretch throughout the galaxies. The result is a cosmic particle accelerator on a scale that dwarfs anything we could ever build. One of the most striking outcomes of this process is the production of high-energy cosmic rays. These particles, traveling at nearly the speed of light, can escape the galaxies and travel vast distances through space. When they collide with other particles or magnetic fields, they emit radiation across the electromagnetic spectrum, from radio waves to gamma rays. This radiation provides astronomers with valuable clues about the conditions within the Antennae Galaxies and the mechanisms driving particle acceleration. The Antennae Galaxies also host regions where supernova explosions and the jets from supermassive black holes contribute to particle acceleration. When a massive star explodes as a supernova, it sends shock waves rippling through the surrounding gas, further accelerating particles. Similarly, the jets emitted by the galaxy's supermassive black holes can act as particle accelerators, propelling particles to even higher energies. These processes create a dynamic environment where particles are continuously being energized and ejected into space. Studying these cosmic particle accelerators helps scientists understand not only the Antennae Galaxies but also the broader universe. High-energy particles play a crucial role in shaping the interstellar medium, influencing star formation and even affecting the evolution of galaxies. By observing the radiation emitted by these particles, astronomers can piece together the complex interactions occurring within the Antennae Galaxies and gain insights into the fundamental physics of particle acceleration. As we continue to explore the Antennae Galaxies, their role as natural particle accelerators reminds us of the incredible forces at work in the universe. These galaxies are not just colliding, they are transforming, creating, and accelerating particles in ways that challenge our understanding of physics. Next, we'll delve into how the Antennae Galaxies are evolving due to their collision and what this means for their future. Now, let's turn our attention to the ongoing evolution of the Antennae Galaxies, a process that is reshaping these cosmic giants in profound ways. The collision between the two galaxies is not just a fleeting event. It's a transformative journey that is altering their structure, composition, and future trajectory. As the galaxies continue to merge, their evolution offers a fascinating glimpse into how such cosmic encounters shape the universe. The collision has triggered a cascade of changes, from the formation of new stars to the redistribution of gas and dust. Over time, the gravitational forces at play will cause the galaxies to fully merge, creating a single, larger galaxy. This process, while chaotic, follows a predictable pattern seen in other galactic collisions. The intense star formation we've discussed earlier is just one phase of this evolution. As the galaxies continue to merge, the rate of star formation will eventually slow down, and the new galaxy will settle into a more stable state. One of the most intriguing aspects of this evolution is the fate of the supermassive black holes at the cores of the two galaxies. Currently, they orbit each other in a gravitational dance, but as the galaxies merge, these black holes will eventually collide and merge as well. This event will release an enormous amount of energy, potentially creating ripples in space-time known as gravitational waves. The merger of these black holes will mark a significant milestone in the galaxy's evolution, shaping the structure of the new galaxy that emerges. The redistribution of gas and dust during the collision also plays a critical role in the galaxy's evolution. As material is flung outward by tidal forces, it forms the spectacular tidal tails we've observed. Over time, some of this material will fall back into the new galaxy, fueling future star formation, while the rest may be lost to intergalactic space. This process not only influences the galaxy's structure, but also affects their chemical composition, enriching the interstellar medium with heavier elements forged in stars and supernova. Looking ahead, the Antennae Galaxies will continue to evolve for hundreds of millions of years. The final product of this merger will likely be an elliptical galaxy, a type of galaxy characterized by its smooth, featureless appearance and older stellar population. This transformation highlights the dynamic nature of the universe, where even the largest structures are constantly changing and evolving. Understanding the evolution of the Antennae Galaxies provides valuable insights into the life cycle of galaxies. It shows how collisions and mergers can drive the formation of new stars, reshape galactic structures, and even influence the distribution of matter in the universe. As we observe this cosmic dance, we gain a deeper appreciation for the forces that shape the cosmos and the intricate processes that govern galactic evolution. Next, we'll explore how the star formation rates in the Antennae Galaxies compare to those in other galaxies and what makes them so unique. Now, shifting our focus to the star formation rates in the Antennae Galaxies, we uncover another layer of their cosmic uniqueness. These galaxies are not just colliding, they are bursting with new stars at a rate that far surpasses that of most other galaxies. In fact, the Antennae Galaxies are producing stars at a staggering pace, making them one of the most prolific star-forming regions in the observable universe. But what exactly sets their star formation rates apart from those in other galaxies? To put it into perspective, the Antennae Galaxies are forming stars at a rate roughly 10 times higher than that of our own Milky Way. While the Milky Way creates about 1 to 2 new stars per year, the Antennae Galaxies churn out dozens, if not hundreds, of new stars annually. This hyperactive star formation is a direct result of the ongoing collision between the two galaxies. The immense gravitational forces at play compress vast clouds of gas and dust, triggering the birth of countless stars in a process known as starburst activity. In contrast, more tranquil galaxies, like spiral galaxies in isolation, tend to have much lower star formation rates. These galaxies often follow a steady, predictable pattern of star birth, driven by internal processes such as the rotation of their spiral arms. However, the Antennae Galaxies are anything but tranquil. Their chaotic environment, fueled by the collision, creates conditions ripe for rapid and intense star formation. This makes them a prime example of what astronomers call starburst galaxies, where star formation occurs at an exceptionally high rate over a relatively short period. Another factor that sets the Antennae Galaxies apart is the sheer scale of their star-forming regions. These areas, often referred to as superstar clusters, are densely packed with young, massive stars that shine brightly and burn through their fuel quickly. In comparison, star-forming regions in more stable galaxies tend to be smaller and less concentrated, producing fewer stars over longer timescales. The Antennae Galaxies, however, are a cosmic factory, churning out stars in vast quantities and at an unprecedented pace. Interestingly, the high star formation rates in the Antennae Galaxies also have long-term consequences. While the current burst of star formation is spectacular, it is not sustainable indefinitely. Over time, the galaxies will exhaust their supply of gas and dust, leading to a decline in star formation. This eventual slowdown is a natural part of the galactic life cycle, but it highlights the transient nature of such intense activity. In contrast, galaxies with lower star formation rates, like elliptical galaxies, often have older stellar populations and less active star-forming regions, reflecting a more settled and evolved state. By comparing the star formation rates in the Antennae Galaxies to those in other galaxies, we gain a deeper understanding of how cosmic events like collisions can dramatically alter a galaxy's evolution. The Antennae Galaxies serve as a vivid reminder that the universe is a dynamic and ever-changing place, where even the most massive structures are shaped by the forces of creation and destruction. Next, we'll explore the evidence of cosmic recycling in the Antennae Galaxies and its importance for galactic evolution. Now, let's turn our attention to a fascinating process that keeps the Antennae Galaxies alive and evolving: cosmic recycling. This phenomenon is not just a cosmic curiosity, it's a vital mechanism that fuels the ongoing transformation of these colliding galaxies. But what exactly is cosmic recycling, and how does it work in the Antennae Galaxies? Cosmic recycling refers to the process by which material from dying stars is expelled back into space, only to be reused in the formation of new stars, planets, and other celestial objects. In the Antennae Galaxies, this process is happening on an extraordinary scale. When massive stars reach the end of their lives, they often explode as supernova, scattering their enriched material across the galaxy. This material, rich in heavy elements like carbon, oxygen, and iron, mixes with the surrounding gas and dust, creating the building blocks for future generations of stars and planets. One of the most compelling pieces of evidence for cosmic recycling in the Antennae Galaxies comes from observations of their supernova remnants. These remnants, the glowing shells of gas left behind after a star explodes, are scattered throughout the galaxies. By studying the composition of these remnants, astronomers have detected high concentrations of heavy elements, which are clear indicators of recycled material. These elements, forged in the hearts of dying stars, are now being incorporated into new star-forming regions, ensuring that the cycle of creation continues. Another key piece of evidence lies in the galaxy's star-forming regions themselves. The Antennae Galaxies are home to some of the most active and massive star-forming regions in the universe, and these regions are teeming with recycled material. Observations using infrared and radio telescopes have revealed that the gas and dust in these areas contain significant amounts of heavy elements, further supporting the idea that cosmic recycling is at work. This recycled material not only fuels the formation of new stars but also influences their composition, leading to the creation of stars with unique chemical signatures. The importance of cosmic recycling in the Antennae Galaxies cannot be overstated. Without this process, the galaxies would eventually exhaust their supply of raw materials, bringing star formation to a halt. Instead, cosmic recycling ensures that the galaxies remain vibrant and dynamic, continuously transforming and evolving. This process also plays a crucial role in the broader context of galactic evolution. By recycling material, the Antennae Galaxies contribute to the enrichment of the universe, spreading heavy elements that are essential for the formation of planets and, ultimately, life. In contrast to more stable galaxies where cosmic recycling occurs at a slower pace, the Antennae Galaxies are a hotbed of activity. Their ongoing collision has created the perfect conditions for this process to thrive, making them a prime example of how cosmic recycling shapes the evolution of galaxies. As we continue to study these remarkable galaxies, we gain a deeper understanding of the intricate processes that drive the life cycle of stars and galaxies alike. Next, we'll explore the evidence for galactic winds in the Antennae Galaxies and their impact on star formation. Now, shifting our focus to another remarkable feature of the Antennae Galaxies, let's explore the evidence for galactic winds and their profound influence on star formation. Galactic winds are powerful streams of gas and particles that flow outward from a galaxy, driven by the energy released from supernova and the intense radiation of young, massive stars. In the Antennae Galaxies, these winds are not just a side effect of cosmic activity, they are a driving force shaping the galaxy's evolution. One of the most compelling pieces of evidence for galactic winds in the Antennae Galaxies comes from observations of their X-ray emissions. Telescopes like the Chandra X-ray Observatory have detected vast regions of hot gas extending far beyond the galaxy's visible structures. These X-ray emissions are a telltale sign of galactic winds, as they reveal the presence of high-energy gas being pushed outward by the combined forces of supernova explosions and stellar radiation. The sheer scale of these winds is staggering, with some extending tens of thousands of light-years into intergalactic space. Another key piece of evidence lies in the galaxy's star-forming regions. As galactic winds sweep through these areas, they carry away vast amounts of gas and dust, which might otherwise collapse to form new stars. This process, known as feedback, plays a crucial role in regulating star formation. While it might seem counterintuitive, this feedback is essential for maintaining balance within the galaxies. Without it, star formation could spiral out of control, depleting the galaxy's resources too quickly. Instead, galactic winds help ensure that star formation occurs at a sustainable rate, allowing the galaxies to evolve over billions of years. The impact of galactic winds on star formation is further highlighted by the distribution of gas and dust within the Antennae Galaxies. Observations using radio and infrared telescopes have shown that the winds create vast cavities and bubbles in the interstellar medium. These structures are not empty voids, but rather regions where the gas has been pushed aside, creating pockets of lower density. Within these pockets, star formation can occur more efficiently as the remaining gas is compressed and heated by the winds. This process leads to the formation of massive star clusters, some of which are among the brightest and most active in the universe. Galactic winds also play a critical role in enriching the intergalactic medium with heavy elements. As the winds carry gas and dust away from the galaxies, they transport elements like carbon, oxygen, and iron into the surrounding space. These elements, forged in the hearts of stars and dispersed by supernova, are essential for the formation of planets and, ultimately, life. In this way, the Antennae Galaxies are not just shaping their own future, but also contributing to the chemical evolution of the universe. The evidence for galactic winds in the Antennae Galaxies underscores their importance as a dynamic and transformative force. By regulating star formation and enriching the cosmos, these winds ensure that the galaxies remain vibrant and ever-changing. As we continue to study these cosmic phenomena, we gain a deeper appreciation for the intricate processes that govern the life cycle of galaxies. Next, we'll delve into the interactions between the supermassive black holes at the cores of the Antennae Galaxies and their influence on the surrounding regions. Now, turning our attention to the heart of the Antennae Galaxies, we encounter one of the most fascinating and powerful phenomena in the cosmos: the interactions between the supermassive black holes at the cores of these colliding galaxies. These black holes, each millions of times more massive than our Sun, are locked in a gravitational dance that shapes the very fabric of their surroundings. Their influence extends far beyond their immediate vicinity, creating ripples that affect star formation, gas dynamics, and even the galaxy's ultimate fate. At the center of each galaxy lies a supermassive black hole, and as the Antennae Galaxies continue their collision, these two titans are drawn closer together. Their immense gravitational pull not only warps space-time, but also generates intense radiation and powerful jets of particles that shoot out at nearly the speed of light. These jets, often stretching thousands of light-years, can heat surrounding gas to millions of degrees, preventing it from cooling and collapsing to form new stars. This process, known as feedback, plays a critical role in regulating star formation and maintaining the delicate balance within the galaxies. One of the most striking effects of these black hole interactions is the creation of vast shock waves that ripple through the interstellar medium. As the black holes orbit each other, their gravitational forces stir up the surrounding gas, creating turbulence and triggering bursts of star formation in some regions while suppressing it in others. This chaotic environment leads to the formation of massive star clusters and supernova explosions, further enriching the galaxies with heavy elements and shaping their evolution. The interaction between the black holes also produces gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity. While these waves are incredibly faint by the time they reach Earth, they carry valuable information about the black hole's masses, spins, and orbital dynamics. Future observatories like the Laser Interferometer Space Antenna, or LISA, aim to detect these waves, providing unprecedented insights into the behavior of supermassive black holes in colliding galaxies. As the black holes spiral closer together, they are expected to eventually merge, releasing an enormous burst of energy in the form of gravitational waves and electromagnetic radiation. This merger will mark a pivotal moment in the evolution of the Antennae Galaxies, potentially triggering a new wave of star formation or even ejecting the resulting black hole from the galactic center. Such events are rare and dramatic, offering a glimpse into the extreme processes that shape the universe. The interactions between the supermassive black holes in the Antennae Galaxies are a testament to the dynamic and ever-changing nature of the cosmos. By studying these phenomena, we not only deepen our understanding of black holes, but also gain valuable insights into the life cycle of galaxies. Next, we'll explore the unique composition of cosmic dust in the Antennae Galaxies and how it contributes to their mysterious beauty. Shifting our focus to the intricate details of the Antennae Galaxies, we now turn to the cosmic dust that fills their vast expanse. This dust, far from being ordinary, holds secrets that reveal the history and evolution of these colliding galaxies. Unlike the dust we find on Earth, cosmic dust in the Antennae Galaxies is composed of tiny particles of carbon, silicon, and other heavy elements, forged in the hearts of dying stars and scattered across space by supernova explosions. These particles, though minuscule, play a crucial role in shaping the galaxy's appearance and behavior. The origins of this cosmic dust are deeply tied to the life cycles of stars. When massive stars reach the end of their lives and explode as supernova, they release vast amounts of material into space, including the elements that form cosmic dust. In the Antennae Galaxies, the frequent supernova explosions resulting from their intense star formation create an abundance of this dust. Over time, these particles accumulate, forming dense clouds that obscure parts of the galaxies and influence the formation of new stars and planets. One of the most fascinating aspects of the cosmic dust in the Antennae Galaxies is its unique composition. Unlike dust in common galaxies, the dust here is enriched with heavier elements like iron, magnesium, and even traces of organic molecules. This enrichment is a direct result of the galaxy's violent history of collisions and star formation. As stars are born and die in rapid succession, they continuously recycle material, adding new layers of complexity to the dust's makeup. These dust clouds are not just passive observers in the galaxy's evolution, they actively participate in shaping their environment. By absorbing and scattering light, cosmic dust affects how we see the Antennae Galaxies, creating the dark lanes and glowing regions visible in telescopic images. Additionally, the dust plays a critical role in cooling the interstellar gas, allowing it to collapse and form new stars. Without this dust, the process of star formation would be far less efficient, and the galaxies would look very different. The study of cosmic dust in the Antennae Galaxies also provides clues about the early universe. The heavy elements found in this dust were not present in the universe's infancy, but were created over billions of years through the life cycles of stars. By analyzing the composition and distribution of this dust, astronomers can piece together the history of star formation and chemical enrichment in these galaxies, offering insights into how galaxies evolve over time. As we continue to explore the Antennae Galaxies, the cosmic dust serves as a reminder of the intricate connections between stars, galaxies, and the universe itself. Next, we'll delve into the long-term effects of the galactic collision and how it has shaped the Antennae Galaxies into the awe-inspiring structures we observe today. Now, let's turn our attention to the lasting impact of the galactic collision that has shaped the Antennae Galaxies into the cosmic spectacle we see today. The aftermath of this colossal event is not just a fleeting moment in time, but a continuous process that has left an indelible mark on these galaxies. Over hundreds of millions of years, the collision has triggered a cascade of changes, from the formation of new stars to the reshaping of entire galactic structures. One of the most significant long-term effects is the ongoing star formation that continues to light up the Antennae Galaxies. The collision compressed vast clouds of gas and dust, creating the perfect conditions for new stars to ignite. These regions of intense star birth, often referred to as starburst regions, are scattered throughout the galaxies, producing stars at a rate far exceeding that of common galaxies like our Milky Way. This relentless star formation has not only altered the galaxy's appearance but also enriched them with heavy elements, further fueling the cycle of creation. The collision has also left its mark on the galaxy's structure. The once distinct spiral arms of the two galaxies have been stretched and twisted into the iconic antennae shape, giving the galaxies their name. These tidal tails, composed of stars, gas, and dust, stretch across vast distances, serving as a visible reminder of the violent encounter. Over time, these tails will gradually dissipate, but their remnants will continue to influence the galaxy's evolution. Another lasting effect is the gravitational interplay between the two supermassive black holes at the galaxy's cores. As the galaxies merged, their black holes began a slow dance, gradually spiraling closer together. This process has created powerful gravitational waves and influenced the distribution of stars and gas in the surrounding regions. Eventually, these black holes may merge, releasing an enormous burst of energy that will further reshape the galaxies. The collision has also triggered galactic winds, powerful outflows of gas and dust that sweep through the galaxies. These winds carry material away from the star-forming regions, redistributing it across the galaxies and even into intergalactic space. This process not only regulates star formation but also enriches the surrounding environment with heavy elements, contributing to the cosmic recycling of matter. As we look to the future, the Antennae Galaxies will continue to evolve. The collision has set them on a path of transformation, one that will eventually lead to the formation of a single, larger galaxy. This new galaxy will bear the scars of its violent past, but it will also be a testament to the dynamic and ever-changing nature of the universe. The story of the Antennae Galaxies is far from over, and each new observation brings us closer to understanding the full scope of their cosmic journey. Next, we'll explore how star clusters form in the chaotic environment of these colliding galaxies. Now, shifting our focus to the heart of the chaos, let's explore how star clusters come to life within the turbulent environment of the Antennae Galaxies. Unlike the relatively calm and orderly star formation we see in galaxies like the Milky Way, the Antennae Galaxies offer a front-row seat to a cosmic frenzy where star clusters are born amidst the chaos of colliding gas clouds and swirling debris. In this dynamic setting, the collision of the two galaxies has created pockets of extreme pressure and density within the interstellar gas. These regions act as cosmic nurseries where gravity takes hold and pulls together vast amounts of gas and dust. As these clouds collapse under their own weight, they fragment into smaller clumps, each of which can give rise to dozens or even hundreds of stars. These newborn stars, bound together by gravity, form what we call star clusters. What makes the Antennae Galaxies particularly fascinating is the sheer scale and intensity of this process. The collision has triggered a burst of star formation so intense that it produces not just individual stars but entire clusters at an astonishing rate. These clusters range in size from small, compact groups of a few dozen stars to massive globular clusters containing hundreds of thousands of stars. Each cluster tells a story of the chaotic conditions that shaped it, with some clusters forming in the dense cores of gas clouds while others emerge from the turbulent tidal tails stretching across the galaxies. The environment in which these clusters form is far from stable. The constant gravitational tug of war between the two galaxies, combined with the powerful forces of supernova explosions and galactic winds, creates a volatile mix. This turbulence can disrupt the formation of clusters, scattering stars or even tearing clusters apart before they fully mature. Yet, despite these challenges, many clusters manage to survive, becoming long-lasting structures that endure for billions of years. One of the most intriguing aspects of star cluster formation in the Antennae Galaxies is the diversity of clusters that emerge. Some are young and bright, filled with massive, hot stars that burn through their fuel quickly and end their lives in spectacular supernova explosions. Others are older and more stable, with stars that have settled into a quieter existence. This mix of ages and types provides astronomers with a unique opportunity to study the life cycle of star clusters in an environment that is both extreme and dynamic. As we continue to observe the Antennae Galaxies, we gain new insights into how star clusters form and evolve in such chaotic conditions. These clusters are not just beautiful cosmic objects, they are also key to understanding the broader processes that shape galaxies. Next, we'll delve into the origins of cosmic rays in the Antennae Galaxies and how these high-energy particles are accelerated to incredible speeds. Now, let's turn our attention to the high-energy particles racing through the Antennae Galaxies' cosmic rays. These mysterious particles, traveling at nearly the speed of light, are one of the most energetic phenomena in the universe. But where do they come from, and how do they shape the environment of these colliding galaxies? Cosmic rays are primarily born from some of the most violent events in space. In the Antennae Galaxies, the collision of two massive galaxies creates a perfect storm of activity, producing shock waves and intense magnetic fields. These conditions act like natural particle accelerators, propelling charged particles such as protons and electrons to incredible speeds. Supernova explosions, which are frequent in the Antennae Galaxies due to their intense star formation, are another major source of cosmic rays. When a massive star explodes, it sends out shock waves that can accelerate particles to near light speeds, launching them into the surrounding space. But the story doesn't end there. The supermassive black holes at the cores of the Antennae Galaxies also play a role in generating cosmic rays. As matter spirals into these black holes, it heats up and emits powerful jets of particles. These jets, stretching across thousands of light years, can accelerate particles to extreme energies, contributing to the cosmic ray population. The combination of supernova, galactic winds, and black hole activity makes the Antennae Galaxies a cosmic ray powerhouse. Once these high-energy particles are unleashed, they have a profound impact on the interstellar medium, the gas and dust that fills the space between stars. Cosmic rays can ionize this gas, stripping electrons from atoms and creating a more electrically charged environment. This ionization process can influence star formation by altering the temperature and pressure of gas clouds, making it easier or harder for new stars to form. Additionally, cosmic rays can heat the interstellar medium, preventing it from cooling and collapsing into new stars. The presence of cosmic rays also affects the chemical composition of the galaxies. As these particles collide with atoms in the interstellar medium, they can trigger nuclear reactions, creating heavier elements. This process, known as spallation, contributes to the enrichment of the galaxies with elements like lithium, beryllium, and boron. Over time, these elements become part of new stars and planets, shaping the evolution of the galaxies. Studying cosmic rays in the Antennae Galaxies gives us a unique window into the high-energy processes that drive galactic evolution. These particles are not just a byproduct of cosmic chaos, they are active participants in shaping the galaxies we see today. Next, we'll explore the complex magnetic fields that weave through the Antennae Galaxies and their role in shaping these cosmic phenomena. Now, let's shift our focus to the invisible forces that weave through the Antennae Galaxies, their magnetic fields. These vast, intricate networks of magnetic energy are not just passive features. They play a crucial role in shaping the galaxy's structure and behavior. Magnetic fields in the Antennae Galaxies are far from uniform. They twist, stretch, and tangle as the two galaxies collide, creating a chaotic yet fascinating cosmic tapestry. One of the most striking aspects of these magnetic fields is their strength. In the Antennae Galaxies, the collision has amplified magnetic forces, making them some of the most powerful observed in the universe. These fields are generated by the motion of charged particles, such as electrons and protons, which are abundant in the turbulent environment of the colliding galaxies. As these particles move, they create electric currents, which in turn produce magnetic fields. The constant churning of gas, dust, and stars during the collision further intensifies these fields, creating a dynamic and ever-changing magnetic landscape. These magnetic fields have a profound impact on the galaxy's evolution. For instance, they influence the movement of cosmic rays, guiding these high-energy particles along their twisted path. This interaction can shape where cosmic rays deposit their energy, affecting the ionization and heating of the interstellar medium. Magnetic fields also play a key role in star formation. They can either support or hinder the collapse of gas clouds depending on their orientation and strength. In some regions, magnetic pressure can prevent gas from collapsing into stars, while in others, it can channel material into dense filaments, sparking the birth of new stars. Another fascinating effect of these magnetic fields is their ability to shape the galaxy's structure on a large scale. The tidal tails, those long streams of stars and gas stretching out from the galaxies, are not just shaped by gravity. Magnetic fields also contribute to their formation and stability. By exerting pressure on the gas and dust within these tails, magnetic fields help maintain their structure over vast distances, even as they stretch across millions of light years. The study of magnetic fields in the Antennae Galaxies also provides insights into the broader universe. By understanding how these fields form and evolve during galactic collisions, scientists can better grasp the role of magnetism in shaping other galaxies and even the cosmic web itself. The Antennae Galaxies serve as a natural laboratory, offering a glimpse into the complex interplay between magnetic fields, gravity, and the interstellar medium. As we continue to unravel the mysteries of these magnetic fields, one thing becomes clear: they are not just a backdrop to the drama of galactic collisions. They are active participants shaping the fate of stars, gas, and even the galaxies themselves. Next, we'll delve into the remnants of supernova explosions and how they leave their mark on the Antennae Galaxies. Now, let's turn our attention to the echoes of cosmic explosions that linger in the Antennae Galaxies, the remnants of supernovas. These remnants are the aftermath of some of the most violent and energetic events in the universe, where massive stars end their lives in spectacular fashion. When a star exhausts its nuclear fuel, it collapses under its own gravity and then explodes, scattering its outer layers into space at incredible speeds. What remains is a glowing shell of gas and dust, rich with heavy elements forged in the heart of the star. In the Antennae Galaxies, supernova remnants are particularly fascinating because of the intense star-forming activity taking place. The collision of the two galaxies has triggered a surge in star birth, and with it, a corresponding increase in star death. As massive stars live fast and die young, their explosive ends leave behind intricate structures that tell the story of their final moments. These remnants are not just cosmic debris, they are treasure troves of information about the life cycles of stars and the chemical evolution of galaxies. One of the key features of supernova remnants in the Antennae Galaxies is their ability to enrich the surrounding interstellar medium. When a star explodes, it releases elements like carbon, oxygen, silicon, and iron into space. These elements, created through nuclear fusion during the star's life and in the explosion itself, become the building blocks for new stars, planets, and even life. The remnants act as cosmic recyclers, spreading these essential ingredients throughout the galaxies. The shock waves from supernova explosions also play a crucial role in shaping their environment. As these waves travel through the interstellar medium, they compress gas and dust, triggering the formation of new stars. This process creates a feedback loop where the death of one generation of stars fuels the birth of the next. In the Antennae Galaxies, this cycle is amplified by the ongoing collision, making supernova remnants a driving force behind the galaxy's evolution. Studying these remnants also provides insights into the physics of supernova explosions themselves. By analyzing the light emitted by the remnants, astronomers can determine the energy of the explosion, the elements produced, and the conditions in the surrounding space. This information helps scientists refine their models of how stars explode and how these events influence their host galaxies. Supernova remnants in the Antennae Galaxies are more than just relics of the past. They are active participants in the galaxy's ongoing story. They shape the interstellar medium, drive star formation, and contribute to the chemical diversity of the cosmos. As we explore these remnants, we gain a deeper understanding of the dynamic processes that govern the life and death of stars. Next, we'll uncover how the Antennae Galaxies' cannibalistic tendencies have shaped their structure and evolution over time. Now, let's shift our focus to a phenomenon that has profoundly shaped the Antennae Galaxies' galactic cannibalism. This process, where larger galaxies consume smaller ones, plays a significant role in the structure and evolution of these cosmic giants. In the case of the Antennae Galaxies, their ongoing collision has not only triggered a frenzy of star formation, but also led to the absorption of smaller satellite galaxies, further altering their appearance and behavior. Galactic cannibalism impacts the Antennae Galaxies in several key ways. First, it contributes to the growth of their mass. As the galaxies consume smaller neighbors, they incorporate their stars, gas, and dark matter, effectively becoming larger and more massive over time. This process also redistributes material within the galaxies, creating new structures like tidal tails and streams of stars that stretch across space. These features are visible reminders of the violent interactions that have shaped the galaxy's current form. Another significant impact is on the galaxy's chemical composition. Smaller galaxies often have different elemental abundances compared to larger ones. When the Antennae Galaxies consume these smaller systems, they inherit these unique chemical signatures, enriching their own interstellar medium. This influx of new elements can influence future star formation, as the availability of heavier elements affects the types of stars that can form and the planets that may eventually orbit them. The gravitational interactions during galactic cannibalism also play a crucial role in shaping the galaxy's evolution. As smaller galaxies are pulled into the Antennae Galaxies, their orbits can destabilize, leading to chaotic mergers that stir up gas and dust. This turbulence can trigger bursts of star formation, as we've seen in the Antennae Galaxies, where the collision has created some of the most active star-forming regions in the known universe. Furthermore, galactic cannibalism can influence the supermassive black holes at the centers of the Antennae Galaxies. As smaller galaxies are absorbed, their central black holes may merge with the larger ones, increasing their mass and potentially altering their activity. These mergers can release enormous amounts of energy, affecting the surrounding environment and contributing to the galaxy's overall evolution. the impact of galactic cannibalism extends beyond the galaxies themselves, influencing their place in the cosmic web. By consuming smaller galaxies, the Antennae Galaxies grow in size and influence, altering the gravitational landscape of their local universe. This process is a reminder that galaxies are not static entities but dynamic systems constantly evolving through interactions with their surroundings. As we explore the effects of galactic cannibalism, we gain a deeper understanding of how galaxies grow, change, and interact over billions of years. The Antennae Galaxies serve as a vivid example of this process, offering a glimpse into the complex and often violent history of galactic evolution. Next, we'll delve into the evidence that supports the triggers of star formation in these fascinating galaxies. Now, let's turn our attention to the evidence that sheds light on what triggers the intense star formation in the Antennae Galaxies. One of the most compelling pieces of evidence comes from observations of the galaxy's collision. When two galaxies collide, the gravitational forces at play compress vast clouds of gas and dust, creating the perfect conditions for new stars to form. In the Antennae Galaxies, this process is particularly dramatic, with regions of star formation so dense and active that they outshine entire galaxies. Astronomers have used telescopes like the Hubble Space Telescope and the Atacama Large Millimeter Array to study these star-forming regions in detail. These observations reveal that the collision has triggered shock waves, which travel through the interstellar medium, compressing gas and dust into dense clumps. These clumps, under the influence of gravity, collapse to form new stars. The sheer number of young, hot stars in these regions provides direct evidence of the collision's role in triggering star formation. Another key piece of evidence comes from the distribution of molecular gas in the Antennae Galaxies. Molecular gas, primarily composed of hydrogen, is the raw material for star formation. Observations show that the collision has caused this gas to accumulate in specific areas, creating pockets of high density. These dense regions are where star formation is most active, further supporting the idea that the collision is the primary trigger. Additionally, the presence of supernova remnants in the Antennae Galaxies offers indirect evidence of star formation triggers. Supernova occur when massive stars reach the end of their lives and explode, releasing energy and heavy elements into the surrounding space. These explosions can trigger further star formation by compressing nearby gas clouds. In the Antennae Galaxies, the high rate of supernova indicates a history of intense star formation driven by the ongoing collision. Finally, computer simulations of galactic collisions provide theoretical evidence for how star formation is triggered in the Antennae Galaxies. These simulations replicate the observed conditions, showing how the collision compresses gas and dust, leading to bursts of star formation. The close match between the simulations and real observations strengthens the case for the collision as the primary trigger. Together, these pieces of evidence paint a clear picture of how the collision between the two galaxies has ignited a frenzy of star formation. The Antennae Galaxies serve as a cosmic laboratory, allowing us to study the processes that shape galaxies and the stars within them. Next, we'll explore the evidence for another fascinating phenomenon: cosmic dust storms, and their impact on these dynamic galaxies. Now, let's shift our gaze to another striking feature of the Antennae Galaxies: cosmic dust storms. These massive storms swirling through the galaxies are not just a spectacle to behold, but also play a crucial role in shaping the galaxy's evolution. Evidence for these dust storms comes from observations made by infrared telescopes, which can peer through the obscuring dust to reveal the hidden dynamics at play. One of the most compelling pieces of evidence lies in the infrared glow emitted by the Antennae Galaxies. This glow is a telltale sign of vast amounts of cosmic dust, heated by the intense radiation from newly formed stars. Infrared observations show that the dust is not evenly distributed but instead concentrated in dense, turbulent clouds. These clouds, driven by the gravitational forces of the colliding galaxies, create the chaotic conditions necessary for dust storms to form. Another key piece of evidence comes from the way these dust storms interact with light. As light from stars and other sources passes through the dust, it gets scattered and absorbed, creating dramatic effects on the galaxy's appearance. This phenomenon, known as extinction, is particularly pronounced in the Antennae Galaxies, where dust storms obscure entire regions, making them appear dark and mysterious. Observations of this extinction effect provide direct evidence of the dust storm's presence and intensity. The impact of these dust storms extends beyond mere visibility. They play a significant role in regulating star formation. As dust particles collide and clump together, they can shield regions of gas from the intense radiation of young stars, allowing these regions to cool and collapse into new stars. However, in other cases, the dust storms can also suppress star formation by blocking the light needed to heat and ionize the gas. This dual role makes cosmic dust storms a fascinating and complex element in the galaxy's life cycle. Additionally, the composition of the dust itself offers clues about its origins. Spectroscopic analysis reveals that the dust in the Antennae Galaxies contains a mix of silicates, carbon compounds, and other materials forged in the hearts of dying stars. This suggests that the dust storms are fueled, in part, by the remnants of supernova explosions, adding another layer of complexity to their formation and behavior. Together, these observations paint a vivid picture of cosmic dust storms as dynamic and influential forces within the Antennae Galaxies. They not only shape the galaxy's appearance but also play a pivotal role in their ongoing evolution. Next, we'll delve into the evidence for intense activity in the cores of these galaxies, where supermassive black holes and other phenomena create a cosmic spectacle unlike any other. Now, let's turn our attention to the very heart of the Antennae Galaxies, their cores. These central regions are anything but quiet. In fact, they are bustling with activity, driven by the presence of supermassive black holes and the chaotic forces unleashed by the ongoing galactic collision. Evidence for this intense activity comes from a variety of observations, each revealing a different piece of the puzzle. One of the most striking pieces of evidence is the detection of powerful X-ray emissions emanating from the cores. These X-rays are produced as matter spirals into the supermassive black holes, heating up to incredible temperatures and releasing vast amounts of energy. Observations from space-based telescopes like Chandra have captured these emissions in stunning detail, showing that the cores are not just active but are among the most energetic regions in the entire galaxy pair. Another key indicator of core activity is the presence of relativistic jets. These jets, composed of particles traveling at nearly the speed of light, are launched from the vicinity of the black holes and extend far beyond the galaxies themselves. Radio observations have revealed these jets stretching across thousands of light years, their presence a clear sign of the immense gravitational forces at work in the cores. These jets not only highlight the black hole's influence but also play a role in shaping the surrounding environment, heating gas and triggering star formation in their wake. Infrared observations add another layer to our understanding. The cores of the Antennae Galaxies glow brightly in infrared light, a result of the intense star formation occurring there. This star formation is fueled by the vast amounts of gas funneled into the cores by the collision, creating a chaotic but fertile environment for new stars to form. The infrared glow also reveals the presence of dense dust clouds, which obscure much of the visible light but are themselves a sign of the core's dynamic nature. Spectroscopic studies provide further evidence, revealing the high velocities of gas and stars in the cores. These velocities, often reaching thousands of kilometers per second, are a direct result of the gravitational pull exerted by the supermassive black holes. The motion of this material creates shock waves and turbulence, contributing to the overall activity and complexity of the cores. Together, these observations paint a picture of the galactic cores as regions of extreme energy and motion. They are not just passive centers but active engines driving the evolution of the Antennae Galaxies. Next, we'll explore how these cores act as natural particle accelerators, producing high-energy particles that ripple through the galaxies and beyond. Now, let's delve into one of the most fascinating aspects of the Antennae Galaxies, their role as cosmic particle accelerators. Evidence for this phenomenon comes from multiple observations, each revealing how these galaxies act as natural laboratories for high-energy physics. One of the most compelling pieces of evidence is the detection of cosmic rays, which are high-energy particles traveling through space at nearly the speed of light. These cosmic rays are thought to be accelerated by the intense magnetic fields and shock waves generated by the collision of the two galaxies. Observations from ground-based telescopes and space observatories have detected gamma rays emanating from the Antennae Galaxies. Gamma rays are the most energetic form of light, and their presence suggests that particles within the galaxies are being accelerated to extreme speeds. These particles collide with gas and dust, producing gamma rays as a byproduct. The detection of these gamma rays provides direct evidence that the Antennae Galaxies are acting as cosmic particle accelerators. Another key piece of evidence comes from radio observations, which reveal the presence of synchrotron radiation. This type of radiation is produced when high-energy electrons spiral around magnetic field lines, emitting radio waves in the process. The detection of synchrotron radiation in the Antennae Galaxies indicates that electrons are being accelerated to relativistic speeds, further supporting the idea that these galaxies are natural particle accelerators. Additionally, X-ray observations have shown that the collision between the two galaxies creates shock waves that propagate through the interstellar medium. These shock waves compress gas and magnetic fields, providing the conditions necessary for particle acceleration. The resulting high-energy particles contribute to the overall activity of the galaxies, influencing star formation and the evolution of the galactic environment. Together, these observations provide strong evidence that the Antennae Galaxies are not just colliding galaxies, but also powerful cosmic particle accelerators. This phenomenon highlights the dynamic and energetic nature of these galaxies, offering a glimpse into the processes that shape the universe on a grand scale. Next, we'll explore the final piece of the puzzle, the evidence for the ongoing evolution of the Antennae Galaxies due to their collision. Now, let's turn our attention to the final piece of the puzzle, the evidence for the ongoing evolution of the Antennae Galaxies as a result of their colossal collision. This phenomenon offers a fascinating glimpse into how galaxies transform over time, shaped by the forces of gravity, star formation, and cosmic interactions. One of the most striking pieces of evidence comes from the galaxy's structure itself. The chaotic, intertwined arms and the massive tidal tails stretching across space are clear indicators of a system still in flux, reshaping itself as the collision progresses. Observations of star formation rates provide another critical clue. The Antennae Galaxies are producing stars at an astonishing pace, far exceeding that of most other galaxies. This burst of activity is a direct consequence of the collision, which compresses gas clouds and triggers the birth of new stars. Over time, this intense star formation will gradually slow down as the available gas is depleted, marking a key phase in the galaxy's evolution. Another compelling piece of evidence lies in the distribution of dark matter. Studies have shown that the collision has disrupted the galaxy's dark matter halos, causing them to merge and redistribute. This redistribution influences the galaxy's gravitational fields, affecting the motion of stars and gas. As the galaxies continue to evolve, their dark matter structures will play a crucial role in determining their final shape and stability. The presence of supermassive black holes at the cores of both galaxies also contributes to their ongoing evolution. As these black holes spiral closer together, their gravitational interactions release enormous amounts of energy, further altering the galaxy's structure. Eventually, these black holes are expected to merge, creating a single, even more massive black hole, a process that will leave a lasting imprint on the galaxy's evolution. Finally, the chemical composition of the Antennae Galaxies provides a snapshot of their evolutionary journey. The collision has enriched the galaxies with heavy elements forged in the hearts of stars and dispersed through supernova explosions. This enrichment fuels the formation of new stars and planets, shaping the galaxy's future as they continue to evolve. Together, these observations paint a vivid picture of the Antennae Galaxies as dynamic, evolving systems. Their collision is not just a single event but an ongoing process that will shape their destiny for millions of years to come. This evidence underscores the incredible complexity and beauty of galactic evolution, offering us a front-row seat to one of the universe's most dramatic transformations. As we wrap up our journey through the Antennae Galaxies, it's clear that these colliding giants are a treasure trove of cosmic wonders. From the chaotic dance of supermassive black holes to the explosive bursts of star formation, each phenomenon we've explored reveals a piece of the puzzle in understanding how galaxies evolve. The tidal tails stretching across space, the mysterious radio emissions, and the swirling clouds of cosmic dust all tell a story of transformation and chaos on a scale that's almost beyond comprehension. What makes the Antennae Galaxies truly unique is how they challenge our understanding of the universe. The strange distribution of dark matter, the powerful galactic winds, and the rare gamma ray bursts all point to processes that are still not fully understood. These galaxies are not just colliding, they're rewriting the rules of galactic evolution, offering scientists a front-row seat to one of the most dramatic events in the cosmos. But the mysteries don't end here. The Antennae Galaxies continue to surprise us with new discoveries shedding light on their complex nature. From the evidence of galactic cannibalism to the intricate magnetic fields shaping their structure, every observation raises new questions and deepens the intrigue. So, what do you think about these 50 strange phenomena? Which one fascinates you the most? Let us know in the comments below. We'd love to hear your thoughts. And if you're as captivated by the Antennae Galaxies as we are, don't forget to explore more about these cosmic wonders. The universe is full of mysteries waiting to be uncovered, and the Antennae Galaxies are just the beginning. Thanks for joining us on this incredible journey through space. If you enjoyed this video, make sure to hit the like button, subscribe to our channel, and ring the notification bell so you never miss out on our next cosmic adventure. Until next time, keep looking up. The universe has so much more to reveal.